Picture yourself standing on the surface of the Earth. It feels flat beneath your feet, yet we know our planet is a sphere. Now, imagine a grander deception, one that spans the entirety of cosmic reality. The flatness of our universe represents one of the most profound puzzles in modern physics. When scientists first began measuring the overall geometry of space, they expected to find it curved, either bending back on itself like a sphere or spreading outward in a hyperbolic saddle shape. The mathematics was clear. The universe should be curved. When cosmologists describe the universe as flat, they're referring to its overall geometry on the largest scales. This concept doesn't mean the universe is two-dimensional like a sheet of paper. Instead, it relates to how space itself is shaped and how light travels through it over vast cosmic distances. In a flat universe, parallel lines remain parallel forever, and the angles in a triangle always add up to 180 degrees. This might seem obvious, but on curved surfaces, these rules don't always apply. Imagine drawing a triangle on a sphere like Earth. Its angles would add up to more than 180 degrees. Our best observations, including measurements of the cosmic microwave background radiation, strongly suggest that our universe is indeed flat or very close to it. This flatness has important implications for the universe's fate and its total energy content. A flat universe is also consistent with the idea of cosmic inflation, a period of rapid expansion in the early universe that would have smoothed out any initial curvature. This geometric flatness is a key piece of evidence supporting our current understanding of the universe's history and structure. Our everyday understanding of flatness typically involves smooth, level surfaces, like tabletops or calm lakes. However, in cosmology, a flat universe has a much different meaning. It refers to the overall geometry and curvature of space-time on the largest scales. In a flat universe, parallel lines remain parallel forever, and the angles of a triangle always add up to 180 degrees. This might seem obvious, but on curved surfaces, these rules can change. Imagine drawing lines on a balloon. As parallel lines extend, they eventually meet, unlike on a flat sheet of paper. Observations suggest our universe is indeed flat or very close to it. This flatness extends far beyond what we can see or measure directly. It implies that the density of matter and energy in the universe is precisely balanced, resulting in a geometry that follows Euclidean principles on cosmic scales. The concept of a flat universe has profound implications for the fate of the cosmos. It suggests that the universe might expand forever, albeit at an ever-slowing rate, rather than collapsing back on itself or accelerating its expansion dramatically. This delicate balance between expansion and gravity continues to intrigue cosmologists as they probe the nature of our vast cosmos. The concept of a flat universe emerged in the mid-20th century as cosmologists began to develop more sophisticated models of the cosmos. In the 1960s, theoretical physicists and astronomers started seriously considering the possibility that the universe might be geometrically flat. This idea gained traction as observations of the cosmic microwave background radiation, first discovered in 1964, provided new insights into the early universe. One of the key figures in this development was Russian physicist Yakov Borisovich Zeldovich, who in the late 1960s proposed that the universe might be exactly flat. His work, along with that of other scientists, laid the groundwork for what would become known as the inflationary theory of the universe, developed in the early 1980s. The flat universe model became increasingly favored as it aligned well with emerging theories about cosmic inflation. the idea that the universe underwent a period of rapid expansion in its earliest moments. This theory helped explain why the universe might appear flat, even if it had started with a different geometry. By the late 20th and early 21st centuries, increasingly precise measurements of the cosmic microwave background radiation, particularly from space-based observatories, provided strong evidence supporting the flat universe model. Today, the flat geometry of the universe is a cornerstone of the standard model of cosmology. Though scientists continue to refine their understanding and test this concept with ever more precise observations. The concept of a flat universe emerged from several key observations in cosmology. One of the earliest and most significant pieces of evidence came from measurements of the cosmic microwave background radiation. This faint glow, left over from the early universe, showed remarkably uniform temperatures across the sky. Such uniformity suggested that different regions of the universe had been in thermal contact early in cosmic history, which is most easily explained by a flat geometry. Another crucial observation was the distribution of galaxies on large scales. Surveys mapping the positions of millions of galaxies revealed a pattern consistent with a flat universe. In a curved universe, we would expect to see systematic distortions in the apparent sizes and distributions of distant galaxy clusters. The absence of such distortions pointed towards a flat cosmic geometry. The measured density of matter in the universe also hinted at flatness. Astronomers found that the amount of visible matter fell far short of what was needed for a closed universe. However, when they factored in dark matter and dark energy, the total density approached the critical value required for a flat universe. Precise measurements of the expansion rate of the universe, combined with data on the ages of the oldest stars, further supported the flat universe model. These observations fit well with theoretical predictions for a universe that is neither open nor closed, but precisely balanced on the knife edge of flatness. The flatness of the universe is a fundamental concept in cosmology that directly influences its overall shape. When we talk about a flat universe, we are referring to its geometry on the largest scales. In a flat universe, parallel lines remain parallel forever, and the angles in a triangle add up to exactly 180 degrees. This flatness has profound implications for the shape of the universe as a whole. A flat universe extends infinitely in all directions without curving back on itself. It resembles an endless sheet stretching out in every direction with no boundaries or edges. This contrasts with other possible geometries, such as a closed universe that would curve back on itself like the surface of a sphere, or an open universe that would have a saddle-like shape. Observations from cosmic microwave background radiation and other astronomical data strongly suggest that our universe is indeed flat or very close to it. This flatness is believed to be a result of cosmic inflation, a period of rapid expansion in the early universe that smoothed out any initial curvature. The flatness of the universe also relates to its density. A flat universe has a critical density, meaning it contains just the right amount of matter and energy to keep expanding forever, but at an ever-slowing rate. This delicate balance between the universe expansion and its contents further supports the idea of a vast, possibly infinite, flat cosmic expanse. The flat universe model we currently favor isn't the only possibility scientists have explored. Two other main alternatives have been considered: the closed universe and the open universe. These models differ in their overall geometry and the ultimate fate they predict for our cosmos. In a closed universe, space has a positive curvature, similar to the surface of a sphere. This model suggests that if you travel in a straight line long enough, you would eventually return to your starting point. A closed universe contains a finite amount of matter and would eventually stop expanding and collapse back on itself in a big crunch. An open universe, on the other hand, has a negative curvature, often compared to the shape of a saddle. In this scenario, The universe would continue expanding forever, with the rate of expansion never slowing to zero. The open universe model predicts a cold, dark future as stars burn out and matter becomes increasingly spread out. These alternatives were considered because they naturally arose from the equations of general relativity and the possible values for the density of matter in the universe. Scientists have long sought to determine which model best fits our observations, leading to extensive research and debates in the cosmological community. The concept of cosmic flatness challenges our intuitive understanding of space by revealing that the universe is far more expansive and uniform than we might imagine. When we think of flatness, we often picture a two-dimensional plane, but cosmic flatness refers to the overall geometry and curvature of the entire universe in 3 dimensions. Our everyday experiences lead us to expect that space should have some kind of inherent curvature or shape. We live on a spherical planet, after all, and we're accustomed to the effects of gravity bending space around massive objects. However, on the grandest scales, astronomers have found that the universe appears to be remarkably flat. This flatness means that parallel lines would remain parallel forever, even across vast cosmic distances. It also implies that the density of matter and energy in the universe is precisely balanced, resulting in a total geometry that is neither positively nor negatively curved. This delicate balance is so precise that it has led scientists to question why the universe is so finely tuned. The implications of cosmic flatness extend to the fate of the universe itself. A flat universe is expected to continue expanding forever, albeit at an ever-slowing rate. This challenges earlier models that suggested the universe might eventually collapse back in on itself or expand so rapidly that it would tear itself apart. The concept of cosmic flatness thus reshapes our understanding of both the current state and the ultimate destiny of our universe. Geometry is fundamental to our understanding of the universe's structure. It provides the mathematical framework that allows scientists to describe and analyze the cosmos on both small and large scales. In cosmology, we use geometry to model the curvature of space-time, which is influenced by the distribution of matter and energy throughout the universe. The shape of the universe can be described using 3 basic geometric models: flat, closed, or open. A flat universe extends infinitely in all directions, like a vast sheet of paper. A closed universe is finite but has no boundaries, similar to the surface of a sphere. An open universe is infinite and has a saddle-like shape, curving inward in some directions and outward in others. These geometric models help scientists make predictions about the universe's behavior and future. For instance, the shape of the universe affects how light travels over vast distances, influencing our observations of distant galaxies and the cosmic microwave background radiation. Current observations suggest that our universe is remarkably close to being flat, though slight deviations are still possible. Geometry also plays a crucial role in describing the effects of gravity on spacetime, as outlined in Einstein's theory of general relativity. This theory depicts gravity not as a force, but as a curvature of spacetime caused by massive objects. The more massive an object, the more it warps the fabric of spacetime around it, affecting the paths of light and other objects nearby. Ancient civilizations had diverse and fascinating ideas about the shape of the universe. Many early cultures viewed the Earth as a flat disk at the center of creation, with the sky as a dome or tent-like structure above. The ancient Babylonians imagined the cosmos as a series of layers, with Earth at the bottom and celestial realms stacked above. In ancient Egypt, the sky was often depicted as the goddess Nut arching over the Earth, with the god Geb representing the ground below. This concept of a curved sky persisted in various forms across different cultures. The ancient Greeks made significant strides in understanding cosmic structures. Pythagoras proposed a spherical Earth, and later Greek thinkers expanded this idea to a series of concentric spheres containing the planets and stars. The Maya civilization of Central America conceived of the universe as a layered structure, with the mortal world sandwiched between celestial and underworld realms. In contrast, ancient Indian cosmology described a flat Earth disk surrounded by concentric oceans and continents, with Mount Meru at the center and celestial realms above. These diverse perceptions of the universe reflect the rich imagination and observational skills of our ancestors. While these models may seem simplistic by modern standards, they laid the groundwork for our current understanding of cosmic structures and inspired generations of thinkers to look up and question the nature of our universe. Ancient civilizations developed various models to explain the structure of the universe. One of the earliest and most influential was the geocentric model, proposed by ancient Greek philosophers. This model placed Earth at the center of the universe, with the sun, moon, planets, and stars revolving around it in perfect circular orbits. The Greek astronomer Ptolemy refined this model in the 2nd century, adding complex systems of epicycles to account for the observed retrograde motion of planets. His geocentric model remained the dominant view of the cosmos for over 1,000 years. In the 16th century, Nicholas Copernicus proposed a revolutionary heliocentric model, placing the Sun at the center of the solar system with Earth and other planets orbiting around it. This concept, although more accurate, was initially met with skepticism and resistance from both religious and scientific communities. It was not until the work of Johannes Kepler and Galileo Galilei in the early 17th century that the heliocentric model gained widespread acceptance. Kepler's laws of planetary motion and Galileo's telescopic observations provided strong evidence supporting the sun-centered system, laying the foundation for our modern understanding of the universe's structure. Einstein's theory of general relativity revolutionized our understanding of cosmic geometry by introducing the concept of curved spacetime. Before Einstein, scientists believed space was flat and unchanging, merely a backdrop for celestial events. General relativity showed that space and time are interwoven and can be warped by massive objects. This new perspective revealed that gravity is not a force, but rather the result of massive objects bending the fabric of space-time. Planets and stars create dips in this cosmic fabric, causing other objects to follow curved paths around them. This explains orbital motion and the bending of light near massive bodies, phenomena that Newtonian physics struggled to fully account for. General relativity also predicted the existence of black holes, regions where space-time is so severely curved that nothing, not even light, can escape. It provided a framework for understanding the expansion of the universe and laid the groundwork for modern cosmology. The theory's equations describe how the universe evolves over time, leading to the concept of an expanding universe and the Big Bang model. Einstein's work fundamentally altered our view of the cosmos from a static, flat stage to a dynamic, curved entity. This shift in perspective continues to shape our understanding of the universe's structure, origin, and ultimate fate, making general relativity a cornerstone of modern astrophysics and cosmology. Edwin Hubble's groundbreaking observations in the 1920s fundamentally transformed our understanding of the cosmos. His work with the powerful Hooker telescope at Mount Wilson Observatory led to two monumental discoveries that forever changed our view of the universe. First, Hubble proved that the fuzzy patches of light astronomers had observed in the night sky were not nearby gas clouds within our own galaxy, but distant galaxies in their own right. This revelation expanded the known size of the universe by an enormous factor, showing that our Milky Way was just one of countless galaxies scattered across the vastness of space. Secondly, and perhaps even more profoundly, Hubble discovered that these distant galaxies were moving away from us, and the farther away they were, the faster they appeared to be receding. This observation led to the formulation of Hubble's law and provided the first empirical evidence for an expanding universe. This discovery dealt a fatal blow to the prevailing static universe model and laid the groundwork for the Big Bang theory. These discoveries not only reshaped our cosmic perspective, but also opened up new avenues of research in cosmology and astrophysics. Hubble's work demonstrated that the universe was far larger, more dynamic, and more mysterious than anyone had previously imagined, setting the stage for decades of exploration and discovery that continue to this day. The concept of an expanding universe revolutionized our understanding of cosmic geometry. When Edwin Hubble discovered that distant galaxies were moving away from us at speeds proportional to their distance, it challenged the prevailing notion of a static universe. This observation led cosmologists to reconsider the shape and structure of the cosmos. The expansion of the universe suggested that space itself was stretching, which opened up new possibilities for its overall geometry. Scientists began to explore three main models: flat, closed, and open universes. In a flat universe, parallel lines remain parallel forever, and the universe expands indefinitely. A closed universe is finite and curves back on itself, like the surface of a sphere, potentially leading to a future contraction. An open universe has negative curvature, expanding ever more rapidly. These models were tied to the density of matter in the universe. If the density exceeded a critical value, gravity would eventually halt and reverse the expansion, resulting in a closed universe. If the density was below this critical value, the expansion would continue forever in an open universe. A perfectly balanced density would lead to a flat universe, expanding at an ever-decreasing rate. Observations of cosmic microwave background radiation and large-scale structure in the universe have since provided strong evidence for a flat geometry. However, the discovery of dark energy, which accelerates cosmic expansion, has added new complexities to our understanding of the universe's shape and ultimate fate. If the density exceeded a critical value, gravity would eventually halt and reverse the expansion, resulting in a closed universe. If the density was below this critical value, the expansion would continue forever in an open universe. A perfectly balanced density would lead to a flat universe, expanding at an ever-decreasing rate. Observations of cosmic microwave background radiation and large-scale structure in the universe have since provided strong evidence for a flat geometry. However, the discovery of dark energy, which accelerates cosmic expansion, has added new complexities to our understanding of the universe's shape and ultimate fate. The discovery of the cosmic microwave background radiation in 1965 revolutionized our understanding of cosmic geometry and the structure of the universe. This faint afterglow from the early universe provided crucial evidence supporting the Big Bang theory and offered insights into the shape and evolution of the cosmos. The cosmic microwave background, or CMB, is remarkably uniform in all directions, suggesting that the universe is isotropic and homogeneous on large scales. This observation strongly supports the idea that space itself is flat, rather than curved like a sphere or saddle. The flatness of space has profound implications for the total energy content of the universe and its ultimate fate. Furthermore, tiny fluctuations in the CMB temperature detected by subsequent missions revealed the seeds of cosmic structure. These minute variations in density eventually grew into the galaxies and galaxy clusters we observe today. By analyzing these fluctuations, scientists could determine the relative amounts of normal matter, and dark energy in the universe, shaping our current model of cosmic composition. The CMB also allowed cosmologists to measure the age of the universe with unprecedented accuracy. By combining CMB data with other observations, scientists determined that the universe is approximately 13.8 billion years old, providing a timeline for cosmic evolution and constraining models of the early universe. Space-based telescopes have revolutionized our understanding of the universe's shape by providing unparalleled views of distant cosmic structures. These advanced instruments, orbiting high above Earth's atmosphere, capture pristine images and data free from atmospheric distortions that limit ground-based observations. The Hubble Space Telescope, launched in 1990, has been instrumental in refining our cosmic perspective. Its deep-field observations have revealed the distribution of galaxies across vast cosmic distances, helping scientists map the large-scale structure of the universe. This cosmic web of galaxies, clusters, and filaments has shown us that matter is not uniformly distributed but forms a complex, interconnected network. Another crucial contribution came from the Wilkinson microwave anisotropy probe, which precisely measured the cosmic microwave background radiation. This ancient light, originating shortly after the Big Bang, provides a snapshot of the early universe. The probe's data strongly supports the idea that the universe is flat on the largest scales, rather than curved like a sphere or saddle-shaped. More recently, the Planck Space Observatory has further refined these measurements, confirming the universe's flatness to an even higher degree of accuracy. These space-based observations have been pivotal in shaping our current understanding of cosmic geometry and have provided strong evidence for the lambda cold dark matter model, our current best description of the universe's composition and evolution. The debate over whether the universe is flat or curved has been a central question in cosmology for decades. This fundamental issue sparked intense discussions and research efforts among scientists throughout the 20th century. In the early 1900s, Albert Einstein's theory of general relativity provided a framework for understanding the shape of the universe. His equations allowed for three possible geometries: flat, positively curved like a sphere, or negatively curved like a saddle. Each of these options had profound implications for the nature and fate of the universe. Proponents of a curved universe argued that gravity would inevitably cause space to bend on a cosmic scale. They believed that a closed, positively curved universe would eventually collapse back in on itself in a big crunch, while an open, negatively curved universe would expand forever. Those favoring a flat universe suggested that the total energy of the cosmos was precisely balanced, allowing it to expand indefinitely at an ever-slowing rate. The debate intensified as observational techniques improved. Scientists sought to measure the density of matter in the universe, as this would determine its curvature. However, conflicting data and the discovery of dark matter and dark energy complicated the picture, leading to decades of uncertainty before more precise measurements began to point towards a flat universe. Scientists employ several sophisticated methods to measure the flatness of the universe, each providing crucial data to form a comprehensive understanding. One primary technique involves analyzing the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. By studying minute temperature fluctuations in this ancient light, researchers can deduce the overall geometry of the universe. Another approach utilizes the concept of gravitational lensing, where massive objects bend light from distant sources. By observing how light from far-off galaxies is distorted by intervening matter, scientists can infer the distribution of mass in the universe and, consequently, its overall shape. Astronomers also use type Ia supernovae as cosmic distance markers. These stellar explosions have consistent brightness, allowing researchers to measure vast cosmic distances accurately. By comparing the apparent brightness of these supernovae with their known intrinsic luminosity, scientists can map out the expansion history of the universe and determine its curvature. Additionally, large-scale galaxy surveys play a crucial role in assessing cosmic flatness. By mapping the three-dimensional distribution of galaxies across vast regions of space, researchers can detect subtle patterns that reveal the underlying geometry of the universe. These combined techniques allow scientists to build a robust picture of the universe's shape, consistently pointing towards a remarkably flat cosmos. Astronomers harness the cosmic microwave background as a powerful tool to investigate the geometry of our universe. This ancient light, emanating from all directions in space, provides a snapshot of the early universe when it was merely 380,000 years old. By meticulously analyzing the patterns and characteristics of this primordial radiation, scientists can uncover crucial information about the shape and curvature of space itself. The key lies in the size of the hot and cold spots within the cosmic microwave background. These temperature fluctuations correspond to regions of slightly different densities in the early universe. In a flat universe, these spots would appear to have a specific angular size when viewed from Earth. However, if the universe were curved, either positively like a sphere or negatively like a saddle, these spots would appear larger or smaller than expected. Using precise measurements from satellites and ground-based telescopes, astronomers compare the observed sizes of these fluctuations to theoretical predictions for different universe geometries. The results consistently point towards a remarkably flat universe, aligning closely with the predictions of cosmic inflation theory. This flatness has profound implications for our understanding of the cosmos. It suggests that the universe is likely infinite in extent and that parallel lines would never meet, no matter how far they are extended. The cosmic microwave background thus serves as a cosmic ruler, allowing scientists to measure the very shape of the universe we inhabit. The critical density of the universe is a key concept in cosmology that helps us understand the overall structure and fate of our cosmos. It represents the average density of matter and energy required for the universe to be perfectly balanced between eternal expansion and eventual collapse. This delicate equilibrium is intimately connected to the idea of flatness in the universe. When we talk about flatness in cosmology, we are referring to the overall geometry of space on the largest scales. A flat universe is one where parallel lines remain parallel forever, and the angles in a triangle add up to exactly 180 degrees. This might seem obvious, but on cosmic scales, space can be curved, leading to different geometries. The relationship between critical density and flatness is straightforward. If the actual density of the universe matches the critical density, then the universe is flat. If the density is higher than the critical value, the universe has a positive curvature like the surface of a sphere. Conversely, if the density is lower than the critical value, the universe has a negative curvature, like the surface of a saddle. Current observations suggest that our universe is remarkably close to the critical density, indicating that it is essentially flat. This finding has profound implications for our understanding of cosmic evolution and the long-term fate of the universe, as it suggests a delicate balance between the forces of expansion and gravity on the grandest of scales. Large-scale structure surveys play a crucial role in advancing our understanding of cosmic flatness. These surveys map out the distribution of galaxies and galaxy clusters across vast regions of space, revealing the intricate web of cosmic structure that spans the observable universe. By analyzing the patterns and arrangements of galaxies on enormous scales, scientists can measure the geometry of space itself. These observations provide crucial data about the overall curvature of the universe, which is directly related to its density and energy content. The way galaxies cluster together and form large-scale structures is influenced by the underlying geometry of space-time. One key aspect of these surveys is their ability to measure the baryon acoustic oscillations, which are remnants of sound waves that propagated through the early universe. The characteristic scale of these oscillations serves as a cosmic ruler, allowing researchers to measure distances across the cosmos with remarkable precision. By comparing these measurements to theoretical predictions for different universe geometries, scientists can constrain the curvature of space. The results from large-scale structure surveys consistently support the idea that our universe is remarkably flat on cosmic scales. This flatness aligns with the predictions of inflationary theory and has profound implications for our understanding of the universe's composition, evolution, and ultimate fate. As these surveys continue to expand in scope and precision, they will further refine our knowledge of cosmic flatness and potentially uncover new insights into the nature of dark energy and dark matter. Gravitational lensing observations serve as a powerful tool in our quest to understand the shape of the universe. This phenomenon occurs when massive objects, such as galaxies or galaxy clusters, bend light from distant sources, acting like cosmic magnifying glasses. By studying these distorted images, astronomers can map the distribution of matter throughout space, including the elusive dark matter that makes up a significant portion of the universe's mass. These observations provide crucial data about the large-scale structure of the cosmos. By analyzing the patterns of gravitational lensing across vast regions of space, Scientists can infer the overall geometry and curvature of the universe. The strength and frequency of lensing effects help determine whether space is flat, curved positively like a sphere, or curved negatively like a saddle. Furthermore, gravitational lensing allows astronomers to probe the expansion history of the universe. By measuring how light from distant galaxies is bent and magnified, researchers can gauge the rate of cosmic expansion at different points in time. This information is vital for understanding the shape and fate of the universe, as it reveals how space itself has changed over billions of years. Ultimately, gravitational lensing observations contribute to a comprehensive picture of cosmic structure and evolution. They complement other methods, such as cosmic microwave background measurements and galaxy surveys, to refine our understanding of the universe's shape and its underlying physical properties. This multifaceted approach helps scientists build increasingly accurate models of our cosmos and its future. Type Ia supernovae serve as crucial cosmic tools for scientists exploring the vast reaches of our universe. These stellar explosions occur when white dwarf stars in binary systems accumulate enough mass from their companion stars to trigger a runaway nuclear fusion reaction. What makes these supernovae particularly valuable is their consistent peak brightness, earning them the nickname "standard candles" in astronomical circles. Astronomers leverage this predictable luminosity to measure vast cosmic distances with remarkable precision. By comparing the observed brightness of a Type Ia supernova to its known intrinsic brightness, scientists can calculate how far away the explosion occurred. This technique allows them to map out the three-dimensional structure of the universe on an enormous scale. But these stellar beacons do more than just measure distance. By studying the light from Type Ia supernovae at different distances, scientists have made the groundbreaking discovery that the universe's expansion is accelerating. This observation has profound implications for our understanding of cosmic geometry and the mysterious force known as dark energy. The data from Type Ia supernovae have helped shape our current model of the universe as a flat, expanding space dominated by dark energy. This information, combined with other cosmological observations, allows scientists to probe the very fabric of space-time itself, uncovering the fundamental nature of our cosmic home and its eventual fate. The omega parameter plays a crucial role in our understanding of the universe's shape and ultimate fate. This cosmic parameter represents the density of the universe compared to the critical density needed for a flat geometry. In cosmology, a flat universe is one where parallel lines remain parallel forever, and the rules of Euclidean geometry apply on the largest scales. When the omega parameter equals 1, it indicates a perfectly flat universe. If omega is greater than 1, the universe has positive curvature and is closed, potentially leading to a future big crunch. Conversely, if omega is less than 1, the universe has negative curvature and is open, expanding forever. Current observations suggest that our universe is remarkably close to flat, with an omega value very near 1. This near flatness poses intriguing questions for cosmologists. It requires an explanation for why the universe's density is so precisely balanced. This fine-tuning problem led to the development of inflationary theory, which proposes a period of rapid expansion in the early universe that would naturally lead to flatness. The omega parameter's value also has implications for the universe's long-term evolution and the nature of dark energy. As we continue to refine our measurements of cosmic parameters, the omega value remains a key focus in our quest to understand the fundamental nature of our universe. Our current measurements of the universe's flatness are remarkably precise, thanks to advancements in observational technology and data analysis techniques. Cosmologists have been able to determine that the universe is flat to within a very small margin of error. The primary tool for measuring the universe's flatness is the cosmic microwave background radiation, the afterglow of the Big Bang. By studying the subtle patterns in this radiation, scientists can deduce the overall geometry of the universe. The most recent data from the Planck Space Telescope, combined with other observations, indicates that the universe is flat to within about 0.4% accuracy. This level of precision is truly astounding when we consider the vast scales involved. It means that if we could measure a circle with a diameter as large as the observable universe, its circumference would deviate from what we expect in a perfectly flat geometry by less than the width of a proton. This incredible flatness poses intriguing questions about the early universe and the mechanisms that led to such a precise balance. While these measurements are highly accurate, cosmologists continue to refine their techniques and gather more data. Future missions and observatories may push this precision even further, potentially revealing subtle deviations or confirming the universe's flatness to even greater certainty. The cosmic microwave background radiation is a faint glow of light that fills the entire universe, detectable in every direction we look. This ancient light began its journey across the cosmos about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and allow light to travel freely for the first time. Scientists often describe the cosmic microwave background as the afterglow of the Big Bang, or the oldest light in the universe. It provides us with a snapshot of the early universe, revealing crucial information about its composition, structure, and evolution. This radiation is incredibly uniform, with only tiny fluctuations in temperature across the sky. These minute temperature variations, measured to be around 1 part in 100,000, are immensely important. They represent the seeds of cosmic structure, the earliest hints of the galaxies and galaxy clusters we see today. By studying these fluctuations, cosmologists can test theories about the universe's birth and early moments. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson was a landmark moment in cosmology. It provided strong evidence for the Big Bang theory and has since become one of the most important tools in our quest to understand the universe's origins and evolution. The cosmic microwave background radiation, often referred to as the CMB, was first discovered in 1965 by two American radio astronomers, Arno Penzias and Robert Wilson. Their groundbreaking discovery was largely accidental, occurring while they were working with a sensitive horn antenna at Bell Labs in New Jersey. Penzias and Wilson were initially trying to detect radio waves from the Milky Way galaxy. However, they encountered a persistent background noise that seemed to come from all directions in the sky. This uniform hiss was present day and night and did not change with the seasons. At first, they thought the noise might be caused by interference from New York City or possibly droppings from pigeons nesting in the antenna. After ruling out these and other potential sources of interference, Penzias and Wilson realized they had stumbled upon something far more significant. They consulted with physicist Robert Dicker at nearby Princeton University, who had been searching for evidence of residual radiation from the Big Bang. Dicker immediately recognized that Penzias and Wilson had found precisely what his team had been looking for. This accidental discovery provided crucial evidence supporting the Big Bang theory of the universe's origin. The CMB represents the afterglow of the early universe, dating back to about 380,000 years after the Big Bang. For their discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, forever changing our understanding of the cosmos. The cosmic microwave background, often referred to as the CMB, is considered the oldest light in the universe because it originated shortly after the Big Bang, approximately 380,000 years after the birth of our cosmos. This ancient light represents a pivotal moment in the history of the universe, marking the time when it cooled enough for atoms to form and light to travel freely through space. Before this period, the universe was an opaque soup of hot plasma, too dense for light to move without being constantly scattered. As the universe expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This process, known as recombination, allowed light to travel unimpeded for the first time. The light we observe as the CMB has been traveling through space for nearly 14 billion years. During this immense journey, the expansion of the universe has stretched its wavelength, shifting it from visible light to microwave radiation. This is why we detect it today as a faint glow of microwaves coming from all directions in space. Studying the CMB provides astronomers with a snapshot of the early universe, offering crucial insights into its composition, structure, and evolution. Its discovery and subsequent analysis have been instrumental in supporting the Big Bang theory and shaping our understanding of cosmic history. The cosmic microwave background radiation, often called the CMB, serves as a powerful piece of evidence supporting the Big Bang theory. This faint glow, detectable from all directions in space, represents the oldest light in the universe, dating back to about 380,000 years after the Big Bang. The CMB is essentially the afterglow of the early universe, when it had cooled enough for atoms to form and allow light to travel freely. This radiation has been stretching and cooling as the universe expands, shifting from intense heat to microwave wavelengths we can detect today. What makes the CMB so compelling as evidence is its remarkable uniformity. This consistency aligns perfectly with the idea of a universe that expanded from a single point, as proposed by the Big Bang theory. The tiny temperature fluctuations we observe in the CMB also match predictions about the early universe's density variations, which eventually led to the formation of galaxies and large-scale structures. Furthermore, the spectrum of the CMB follows precisely what we would expect from a cooling, expanding universe that started in an extremely hot, dense state. This alignment between theoretical predictions and observed reality strongly supports the Big Bang model, making the CMB one of the most important discoveries in cosmology. The cosmic microwave background, or CMB, serves as a powerful tool for cosmologists, offering a wealth of information about the early universe. By studying the minute temperature fluctuations in this ancient light, scientists can uncover crucial details about the universe's composition, geometry, and evolution. These temperature variations, though incredibly small, represent areas of slightly different densities in the early universe. They provide a snapshot of the cosmos when it was merely 380,000 years old. From this cosmic portrait, researchers can determine the distribution of matter in the infant universe, which directly influence the formation of galaxies and large-scale structures we observe today. The CMB temperature fluctuations also reveal the relative amounts of normal matter, and dark energy in the universe. By analyzing the size and distribution of these fluctuations, scientists can calculate the universe's curvature, confirming that space is remarkably flat on large scales. This flatness aligns with the theory of cosmic inflation, a period of rapid expansion in the universe's first fraction of a second. Furthermore, the CMB fluctuations allow cosmologists to estimate the universe's age with remarkable precision. They also provide evidence for acoustic oscillations in the primordial plasma, which helps explain the spacing of galaxies in the current cosmos. All these insights derived from the CMB's temperature variations continue to shape and refine our understanding of the universe's history and fundamental nature. Scientists create maps of the cosmic microwave background using specialized telescopes and satellites designed to detect faint microwave radiation. These instruments scan the entire sky, measuring tiny temperature variations in the ancient light that has been traveling through space for over 13 billion years. The data collected by these instruments is processed using complex computer algorithms to filter out interference from our galaxy and other sources. The result is a detailed map showing slight temperature differences across the sky, typically represented by colors ranging from blue for cooler areas to red for warmer regions. These maps of the cosmic microwave background are invaluable to cosmologists as they provide a snapshot of the universe when it was only about 380,000 years old. The patterns of hot and cold spots reveal the distribution of matter in the early universe, showing the seeds of cosmic structure that would eventually grow into the galaxies and galaxy clusters we see today. By analyzing these maps, scientists can determine fundamental properties of the universe, such as its age, composition, and geometry. They can also test theories about cosmic inflation, the nature of dark matter and dark energy, and the overall evolution of the cosmos. The cosmic microwave background maps serve as a powerful tool for understanding the origin and fate of our universe. Acoustic oscillations in the cosmic microwave background are ancient sound waves that echoed through the early universe. These ripples formed when the cosmos was a hot, dense plasma of particles and photons. As the universe expanded and cooled, these sound waves became frozen in time, leaving their imprint on the cosmic microwave background radiation we observe today. These oscillations provide crucial information about the geometry and composition of the universe. By analyzing the size and spacing of these ripples, scientists can determine the curvature of space itself. The pattern we observe in the cosmic microwave background strongly suggests that the universe is flat, meaning parallel lines will always remain parallel, even over vast cosmic distances. The connection between acoustic oscillations and cosmic flatness lies in the way these sound waves propagated through the early universe. In a flat universe, these waves would have traveled specific distances before the universe cooled enough to freeze them in place. The size of these frozen ripples matches what we would expect in a flat universe, providing strong evidence for cosmic flatness. This flatness has profound implications for our understanding of the cosmos. It suggests that the universe is finely balanced between eternal expansion and eventual collapse, hinting at the delicate interplay of matter, energy, and the mysterious force of dark energy that shapes our universe. Our understanding of the cosmic microwave background has grown tremendously since its accidental discovery in 1965. Initially detected as a uniform background radiation, early observations provided crucial evidence for the Big Bang theory. However, as technology advanced, we gained a much more detailed and nuanced picture of this ancient light. Space-based missions like the Cosmic Background Explorer, launched in 1989, revealed tiny temperature fluctuations in the cosmic microwave background. These fluctuations, mere fractions of a degree, offered a glimpse into the early universe's structure. The Wilkinson Microwave Anisotropy Probe, which began its observations in 2001, further refined our measurements, providing a more precise age estimate for the universe and confirming the presence of dark matter and dark energy. The Planck mission, operational from 2009 to 2013, took our understanding to new heights. It produced the highest resolution map of the cosmic microwave background to date, allowing scientists to test and refine models of cosmic inflation and the distribution of matter in the early universe. These observations also helped confirm the standard model of cosmology and provided insights into the universe's geometry and composition. Recent ground-based experiments and upcoming missions promise even more precise measurements. These advancements will help address remaining questions about the early universe, potentially shedding light on the nature of dark matter and dark energy, and possibly revealing signs of primordial gravitational waves. Each technological leap brings us closer to understanding the birth and evolution of our cosmos. Cosmic inflation theory proposes that the early universe underwent a period of rapid expansion shortly after the Big Bang. This expansion occurred faster than the speed of light and lasted for an incredibly brief moment, less than a trillionth of a second. During this fleeting instant, the universe grew exponentially, stretching from a size smaller than a proton to cosmic scales. The theory was developed to explain several puzzling features of our universe, including its remarkable uniformity across vast distances and its nearly flat geometry. Inflation accounts for these observations by suggesting that the entire observable universe originated from a minuscule, homogeneous region that was blown up to cosmic proportions. Cosmic inflation also provides a mechanism for the formation of large-scale structures in the universe. Quantum fluctuations, tiny variations in the fabric of space-time, were stretched to cosmic scales during inflation. These fluctuations later became the seeds for galaxies and galaxy clusters, explaining the cosmic web of structure we observe today. While cosmic inflation theory has gained widespread acceptance among cosmologists, it remains an active area of research. Scientists continue to refine the theory and search for observational evidence to further support or challenge its predictions, making it a cornerstone of modern cosmology. Cosmic inflation provides a compelling explanation for the observed flatness of our universe. This theory proposes that in the earliest moments after the Big Bang, the universe underwent a brief period of exponential expansion. During this fleeting instant, space itself expanded faster than the speed of light, stretching the fabric of the cosmos to an almost inconceivable degree. This rapid expansion had a profound effect on the geometry of space. Any initial curvature or irregularities in the universe were dramatically smoothed out, much like how inflating a balloon stretches its surface, making it appear increasingly flat as it expands. The sheer magnitude of this inflation was so great that it effectively ironed out any cosmic wrinkles, leaving behind a universe that appears remarkably flat on the largest scales. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, strongly support this notion of a flat universe. Measurements show that the overall geometry of space is flat to within a tiny margin of error. Without inflation, achieving such a high degree of flatness would be extremely improbable, requiring an almost impossibly precise balance of matter and energy in the early universe. Inflation not only explains the observed flatness, but also solves other cosmological puzzles, such as the horizon problem and the magnetic monopole problem. It provides a unified framework for understanding the large-scale structure and properties of our universe, making it a cornerstone of modern cosmology. The theory of cosmic inflation was first proposed by American physicist Alan Guth in 1980. Guth developed this groundbreaking idea while studying the early universe and attempting to solve several puzzling problems in cosmology. Cosmic inflation addresses issues like the horizon problem, which questions why distant regions of the universe appear similar despite seemingly having no way to communicate. It also tackles the flatness problem, explaining why the universe's geometry is so close to being flat. Guth realized that a brief period of exponential expansion in the universe's earliest moments could elegantly solve these and other cosmological conundrums. According to the theory, the universe expanded faster than the speed of light for a fraction of a second after the Big Bang. This rapid expansion smoothed out any irregularities and allowed the entire observable universe to originate from a tiny, causally connected region. This explanation provided a framework for understanding the large-scale structure and uniformity we observe in the cosmos today. Guth's proposal revolutionized our understanding of the early universe and has since become a cornerstone of modern cosmology. While the theory has evolved and been refined by other scientists, Guth's initial insight laid the foundation for our current models of the universe's origins and evolution. Inflation theory addresses several key challenges in our understanding of the early universe. This groundbreaking concept proposes that the cosmos underwent a period of incredibly rapid expansion in its first fraction of a second, growing from subatomic scales to cosmic proportions almost instantaneously. One major issue inflation tackles is the horizon problem. Our observations show that distant regions of the universe have remarkably similar temperatures and properties, even though they should never have been in contact under standard cosmological models. Inflation solves this by suggesting these regions were once close enough to interact before being rapidly stretched apart. Another puzzle inflation addresses is the flatness problem. The universe appears to be extraordinarily flat on large scales, which requires incredibly precise initial conditions in traditional models. Inflation naturally produces this flatness by stretching any initial curvature to cosmic scales, much like inflating a balloon smooths out its surface. Inflation also provides a mechanism for the origin of cosmic structure. It proposes that quantum fluctuations present in the minuscule pre-inflation universe were stretched to cosmic scales during the inflationary period. These fluctuations then became the seeds for the formation of galaxies and large-scale structures we observe today, elegantly explaining the universe's rich tapestry of cosmic features. Cosmic inflation provides a compelling explanation for the remarkable uniformity observed in the cosmic microwave background. This theory proposes that in the earliest moments of the universe, just a fraction of a second after the Big Bang, space itself underwent an incredibly rapid expansion. During this brief period, the universe grew exponentially, stretching faster than the speed of light. This rapid expansion had a profound effect on the early universe. It smoothed out any initial irregularities or fluctuations in energy and matter distribution, much like stretching a wrinkled piece of fabric until it becomes nearly flat. As a result, regions of space that were once in close contact and had time to reach thermal equilibrium were suddenly stretched far apart. The cosmic microwave background we observe today is essentially a snapshot of the universe about 380,000 years after the Big Bang, when it had cooled enough for atoms to form and light to travel freely. The uniformity we see in this ancient light is a direct consequence of the smoothing effect of inflation. Without inflation, it would be difficult to explain how regions of the universe that appear to have never been in causal contact could have such similar temperatures and properties. Inflation solves this horizon problem by proposing that these regions were indeed in contact before being rapidly stretched apart, accounting for the observed uniformity across vast cosmic distances. The theory of cosmic inflation, a crucial component of our understanding of the early universe, is supported by several compelling pieces of evidence. One of the most significant is the remarkable uniformity of the cosmic microwave background radiation. This faint afterglow from the early universe shows an almost perfect consistency in temperature across the entire sky, with variations of only about 1 part in 100,000. Such uniformity would be nearly impossible to explain without a period of rapid expansion that smoothed out any initial irregularities. Another key piece of evidence comes from the flatness of space. Observations indicate that the universe is incredibly close to being geometrically flat, which aligns perfectly with the predictions of cosmic inflation. This theory suggests that the rapid expansion would have stretched space to such an extent that any initial curvature would have been flattened out, much like inflating a balloon smooths its surface. The distribution of galaxies and large-scale structures in the universe also supports the inflation theory. The cosmic web of galaxy clusters and filaments we observe today matches the pattern of tiny quantum fluctuations that would have been amplified by inflation in the early universe. This connection between the smallest quantum scales and the largest cosmic structures provides an elegant explanation for the universe's current appearance. Lastly, the absence of magnetic monopoles, which many theories predict should have been produced in abundance in the early universe, can be explained by cosmic inflation. The rapid expansion would have diluted these particles to such an extent that finding one today would be extremely unlikely, aligning with our observations of the universe. Inflation theory provides a compelling explanation for the large-scale structure we observe in the universe today. This theory posits that in the earliest moments after the Big Bang, the universe underwent a brief period of exponential expansion, stretching faster than the speed of light. During this inflationary phase, quantum fluctuations, tiny variations in the distribution of matter and energy, were amplified to cosmic scales. These fluctuations served as the seeds for the formation of galaxies and galaxy clusters we see today. As the universe continued to expand and cool after inflation, these slight irregularities in density grew under the influence of gravity. Over billions of years, areas with slightly higher density attracted more matter, while less dense regions became more empty. This process led to the formation of a cosmic web structure, with galaxies and galaxy clusters forming along filaments of dark matter separated by vast cosmic voids. Inflation theory thus explains both the overall uniformity of the universe on the largest scales and the presence of these intricate structures. Furthermore, inflation theory predicts that the universe should be geometrically flat on large scales, which aligns with observations from cosmic microwave background radiation studies. This flat geometry, combined with the specific pattern of density fluctuations, provides strong support for the inflation model and its predictions about the large-scale structure of the universe. Cosmic inflation theory has been a cornerstone of modern cosmology, but it's not without its challenges. Several alternative theories have emerged to explain the observed flatness of the universe without relying on an inflationary period. One such alternative is the bouncing universe model. This theory proposes that our universe undergoes cycles of expansion and contraction. In this scenario, the flatness we observe today is a natural consequence of the universe having gone through many previous cycles, each one smoothing out any curvature. The idea is that over countless bounces, the universe would tend towards flatness, much like how a wrinkled sheet becomes smoother when stretched repeatedly. Another contender is the ekpyrotic universe theory. This model suggests that our universe resulted from the collision of two three-dimensional worlds in a higher dimensional space. The cosmic flatness we see is explained as an outcome of this collision and the subsequent expansion without the need for an inflationary period. In this view, the flatness is a fundamental property arising from the nature of the universe's birth. String gas cosmology offers yet another explanation. This theory, rooted in string theory, proposes that the early universe was filled with a hot gas of strings. As these strings interacted and the universe cooled, it naturally settled into a flat state. This model suggests that flatness is an inherent property of how the universe emerged from its string-theoretic beginnings, rather than the result of a rapid expansion. Dark energy is a mysterious force that permeates all of space and acts against the pull of gravity. It is believed to be responsible for the accelerating expansion of our universe, pushing galaxies and cosmic structures apart at an ever-increasing rate. The discovery of dark energy came as a surprise to astronomers in the late 1990s. Two independent teams of scientists were studying distant supernovae, powerful stellar explosions used as cosmic distance markers. Dark energy is a mysterious force that permeates all of space and acts against the pull of gravity. It is believed to be responsible for the accelerating expansion of our universe, pushing galaxies and cosmic structures apart at an ever-increasing rate. The discovery of dark energy came as a surprise to astronomers in the late 1990s. Two independent teams of scientists were studying distant supernovae, powerful stellar explosions used as cosmic distance markers. Their goal was to measure how the expansion of the universe changed over time. They expected to find that the expansion was slowing down due to the gravitational pull of matter. However, their observations revealed something unexpected. The universe was not slowing down at all. Instead, it was speeding up. This accelerating expansion could not be explained by known physics, leading to the proposal of a new form of energy that works against gravity on cosmic scales. Since its discovery, dark energy has become one of the most intriguing and perplexing aspects of modern cosmology. It is estimated to make up about 68% of the universe's total energy content, yet its fundamental nature remains a mystery. Scientists continue to study dark energy, hoping to unravel its secrets and better understand the fate of our expanding universe. Dark energy exerts a profound influence on the shape and evolution of the universe, acting as a mysterious force that counteracts gravity on cosmic scales. This enigmatic form of energy permeates all of space, causing the expansion of the universe to accelerate rather than slow down as previously expected. As dark energy pushes the fabric of space-time apart, it shapes the large-scale structure of the cosmos. Galaxies and galaxy clusters are driven farther away from each other at an ever-increasing rate, leading to a universe that becomes more sparse and spread out over time. This expansion affects the distribution of matter, altering the cosmic web of filaments and voids that characterize the universe's structure. The presence of dark energy has significant implications for the ultimate fate of the universe. If dark energy continues to dominate, the expansion will persist indefinitely, potentially leading to a scenario known as the Big Freeze. In this future, galaxies outside our local group will eventually become so distant that they are no longer observable, and the universe will become increasingly cold and diffuse. Understanding dark energy is crucial for cosmologists as they attempt to unravel the mysteries of our universe's past, present, and future. Its discovery has revolutionized our understanding of cosmic evolution, challenging long-held assumptions and opening new avenues of research in the quest to comprehend the fundamental nature of reality. Dark energy and the accelerating expansion of the universe are intimately connected. Scientists discovered this acceleration in the late 1990s when they observed that distant supernovae were farther away than expected. This observation contradicted the long-held belief that the expansion of the universe was slowing down due to gravity. To explain this unexpected acceleration, cosmologists proposed the existence of dark energy. This mysterious force acts in opposition to gravity, pushing the universe apart rather than pulling it together. Dark energy permeates all of space, maintaining a constant density as the universe expands. This means that as the universe grows larger, the total amount of dark energy increases, causing the expansion to speed up over time. Current estimates suggest that dark energy makes up about 68% of the total energy content of the universe. Its effects become more dominant as the universe expands because matter becomes more spread out, while dark energy remains constant throughout space. This shift in the balance between matter and dark energy drives the accelerating expansion we observe today. Despite its crucial role in shaping the evolution and fate of the universe, the true nature of dark energy remains one of the biggest mysteries in modern cosmology. Scientists continue to investigate its properties and origins, hoping to unravel this enigma and better understand the future of our expanding universe. Dark energy profoundly influences our understanding of cosmic flatness, shaping the very fabric of space-time on the grandest scales. This mysterious force, which accounts for about 68% of the energy content in the universe, exerts a repulsive effect that counteracts gravity and drives the accelerating expansion of the cosmos. When cosmologists measure the geometry of space, they find it to be remarkably flat. However, dark energy complicates these measurements. As the universe expands at an ever-increasing rate due to dark energy, it stretches the cosmic web of matter, making the universe appear flatter than it might be in reality. This effect is similar to how blowing up a balloon smooths out its surface, making any curvature less noticeable. Furthermore, dark energy affects the propagation of light across vast cosmic distances. This impacts our observations of distant objects, such as Type I supernovae, which serve as standard candles for measuring cosmic distances. The presence of dark energy causes these objects to appear slightly fainter than expected, influencing our calculations of the universe's geometry. Consequently, scientists must carefully account for the effects of dark energy when interpreting data related to cosmic flatness. This interplay between dark energy and cosmic geometry underscores the complexity of our universe and highlights the ongoing challenges in cosmology as we strive to unravel the nature of this enigmatic force. Dark energy remains one of the most perplexing mysteries in modern cosmology. Scientists have proposed several theories to explain this enigmatic force that appears to be accelerating the expansion of our universe. The leading contender is the cosmological constant, an idea originally proposed by Albert Einstein. This theory suggests that dark energy is an inherent property of space itself, with a constant density throughout the cosmos. As the universe expands, more space comes into existence, creating more dark energy and driving further expansion. Another prominent theory is quintessence, which posits that dark energy is a dynamic field that changes over time and space. Unlike the cosmological constant, quintessence could potentially explain why the expansion of the universe is accelerating at its current rate. Some researchers propose modifications to our understanding of gravity on cosmic scales, suggesting that what we perceive as dark energy might actually be a manifestation of how gravity behaves differently across vast distances. These modified gravity theories aim to explain cosmic acceleration without invoking a new form of energy. Dark energy, the mysterious force causing the accelerated expansion of our universe, is poised to dramatically reshape cosmic structure in the distant future. As this enigmatic energy continues to exert its influence, it will likely cause the universe to expand at an ever-increasing rate, potentially leading to a scenario known as the Big Rip. In this future, dark energy could become so dominant that it overcomes all other forces, including gravity. Galaxies would be pulled apart, followed by solar systems, planets, and eventually even atoms themselves. This process would effectively stretch the fabric of space-time to its breaking point, leaving behind a cold, empty void. However, it's important to note that this is just one possible outcome. Another potential scenario is that dark energy remains constant, leading to a gradual cooling and expansion of the universe without the dramatic tearing apart of matter. This would result in a universe that becomes increasingly sparse and dark over unimaginably long timescales. The ultimate fate of our universe hinges on the true nature of dark energy, which remains one of the biggest mysteries in modern cosmology. As we continue to study this elusive force, we may gain new insights into how it will shape the cosmic landscape in the incredibly distant future. The existence of dark energy is supported by several key observations in cosmology. One of the most compelling pieces of evidence comes from studies of Type Ia supernovae. These stellar explosions serve as cosmic distance markers, allowing astronomers to measure how quickly the universe is expanding at different points in its history. Observations of these supernovae revealed that the expansion of the universe is actually accelerating, contrary to what scientists expected based on the gravitational pull of matter alone. Another line of evidence comes from measurements of the cosmic microwave background radiation, the afterglow of the Big Bang. The patterns observed in this radiation provide information about the geometry and composition of the universe. These measurements indicate that the universe is flat and that ordinary matter and dark matter together account for only about 30% of the total energy density of the universe. This leaves roughly 70% unaccounted for, which is attributed to dark energy. Large-scale structure surveys, which map out the distribution of galaxies across vast distances, also support the existence of dark energy. The way galaxies cluster together and form filaments and voids is influenced by the expansion history of the universe. The observed patterns in these surveys are consistent with a universe dominated by dark energy. Gravitational lensing observations, which detect how light from distant galaxies is bent by the gravity of intervening matter, provide additional support. These observations help map out the distribution of matter in the universe and confirm the proportions of dark matter and dark energy indicated by other methods. Together, these diverse lines of evidence converge on the conclusion that dark energy is a fundamental component of our universe, driving its accelerating expansion. Dark energy poses a profound challenge to our understanding of physics, pushing the boundaries of our knowledge about the fundamental nature of the universe. This mysterious force, which appears to be causing the accelerating expansion of the cosmos, defies explanation within our current framework of physics. The discovery of dark energy came as a shock to scientists. Observations of distant supernovae revealed that the universe is not only expanding, but doing so at an increasing rate. This acceleration contradicts what we would expect from gravity, which should be slowing the expansion down. The force behind this acceleration, which we call dark energy, seems to permeate all of space, exerting a repulsive effect that counteracts gravity on cosmic scales. What makes dark energy so perplexing is its apparent contradiction with our understanding of how energy and matter behave. It seems to have a constant density throughout space, which violates our expectations based on the expansion of the universe. As space expands, the amount of dark energy appears to increase, creating more and more of this mysterious substance out of seemingly nothing. This behavior challenges our notions of energy conservation, a cornerstone principle in physics. Furthermore, attempts to explain dark energy using quantum field theory lead to predictions that are wildly inconsistent with observations, off by a factor of 10 to the power of 120. This enormous discrepancy highlights the deep rift between our current theories of the very large general relativity and the very small quantum mechanics. Dark energy stands as a cosmic signpost, pointing towards a more complete understanding of the universe that has so far eluded us, driving physicists to search for new theories that can bridge this gap in our knowledge. Dark matter is a mysterious substance that permeates the universe, vastly outnumbering the ordinary matter we can see and touch. Unlike normal matter, which interacts with light and other forms of electromagnetic radiation, dark matter remains invisible and undetectable through conventional means. It does not emit, absorb, or reflect light, making it incredibly challenging to study directly. The primary way we know dark matter exists is through its gravitational effects on visible matter. Astronomers observe galaxies rotating faster than they should based on their visible mass alone, and galaxy clusters held together by seemingly invisible forces. These observations point to the presence of an unseen substance exerting gravitational pull. While normal matter is composed of familiar particles like protons, neutrons, and electrons, the exact nature of dark matter remains unknown. Scientists have proposed various candidates, including weakly interacting massive particles and axions, but none have been definitively detected. Dark matter is believed to make up about 85% of all matter in the universe, dwarfing the amount of normal matter. Understanding dark matter is crucial for explaining the structure and evolution of the universe. It plays a vital role in the formation of galaxies and large-scale cosmic structures, acting as a gravitational scaffold around which visible matter coalesces. As scientists continue to probe its nature, dark matter remains one of the most intriguing and important mysteries in modern cosmology. Dark matter plays a crucial role in shaping the large-scale structure and geometry of the universe. This invisible form of matter, which does not interact with light or other forms of electromagnetic radiation, exerts a powerful gravitational influence on visible matter and the fabric of space-time itself. The presence of dark matter affects the distribution of galaxies and galaxy clusters throughout the cosmos. It forms vast web-like structures called cosmic filaments, along which visible matter tends to accumulate. These filaments create a complex network that spans the observable universe, with dense clusters of galaxies forming at the intersections of these cosmic highways. Dark matter's gravitational effects also contribute to the overall curvature of space-time on a cosmic scale. Its distribution and abundance help determine whether the universe has a flat, open, or closed geometry. Current observations suggest that dark matter, combined with dark energy, results in a nearly flat universe, which has profound implications for its long-term fate and evolution. Furthermore, dark matter influences the formation and evolution of cosmic structures over time. Its gravitational pull has been instrumental in the growth of galaxies and galaxy clusters from the small density fluctuations present in the early universe. This process has shaped the cosmic landscape we observe today, creating a universe rich in structure and complexity. Dark matter remains one of the most intriguing mysteries in modern cosmology. Scientists have gathered compelling evidence for its existence through various astronomical observations. One of the strongest pieces of evidence comes from studying the rotation of galaxies. Stars at the outer edges of spiral galaxies move much faster than expected based on the visible mass alone. This suggests the presence of an invisible form of matter exerting gravitational influence. Gravitational lensing provides another crucial line of evidence. When light from distant galaxies passes by massive objects, it bends due to gravity. Astronomers have observed this bending effect to be much stronger than what visible matter alone can explain, indicating the presence of additional unseen mass. The cosmic microwave background, a relic radiation from the early universe, also supports the dark matter hypothesis. Its pattern of temperature fluctuations aligns closely with models that include dark matter, but not with those that exclude it. Additionally, computer simulations of galaxy formation and large-scale structure in the universe match observations much more closely when dark matter is included. While scientists have yet to directly detect dark matter particles, the convergence of evidence from multiple independent sources strongly supports its existence. The search for dark matter continues, with researchers exploring various theories and conducting experiments to unravel this cosmic enigma. Scientists employ various sophisticated methods in their quest to detect dark matter particles. One approach involves using large underground detectors filled with ultra-pure materials like xenon or germanium. These detectors are shielded from cosmic rays and other background radiation, allowing researchers to focus on potential dark matter interactions. When a dark matter particle collides with an atom in these detectors, it should produce a tiny flash of light or a small electrical signal. Highly sensitive instruments are used to capture these faint signals, which could indicate the presence of dark matter. However, these events are extremely rare, requiring long observation periods and extensive data analysis. Another method utilizes particle accelerators to create high-energy collisions that might produce dark matter particles. Scientists then search for missing energy in the collision debris, which could suggest the creation of invisible dark matter particles. Additionally, space-based telescopes and underground neutrino detectors are used to search for indirect evidence of dark matter, such as unusual patterns in cosmic rays or neutrino emissions. Despite these efforts, dark matter remains elusive. Scientists continue to refine their techniques and develop new technologies to increase the chances of detection. The search for dark matter particles represents one of the most challenging and exciting frontiers in modern physics, pushing the boundaries of our understanding of the universe. The cosmic web is the vast, intricate structure that forms the backbone of our universe. It consists of an enormous network of interconnected filaments and clusters stretching across the cosmos. These filaments are made up of galaxies and galaxy clusters, forming a web-like pattern that spans billions of light years. Dark matter plays a crucial role in shaping the cosmic web. Although invisible to our telescopes, dark matter exerts a powerful gravitational influence on visible matter. It acts as a scaffolding, guiding the formation and distribution of galaxies and galaxy clusters along its unseen threads. The densest regions of dark matter form the nodes of the cosmic web, where massive galaxy clusters congregate. These clusters are connected by long filaments of dark matter, along which galaxies and smaller clusters are strung like beads on a cosmic necklace. Between these filaments lie vast, nearly empty voids, creating a striking contrast in the universe's structure. By mapping the distribution of visible galaxies, astronomers can infer the underlying dark matter structure of the cosmic web. This relationship between visible matter and dark matter provides crucial insights into the evolution and large-scale structure of our universe, helping scientists understand how galaxies form and cluster over cosmic time. Dark matter plays a crucial role in shaping the structure and evolution of galaxies. This mysterious substance, which does not interact with light or other forms of electromagnetic radiation, exerts a powerful gravitational influence on visible matter. In the early universe, dark matter formed vast, invisible scaffolds known as halos. These dark matter halos acted as gravitational wells, drawing in normal matter such as gas and dust. As this material accumulated within the dark matter halos, it began to form the first stars and galaxies. The additional gravitational pull of dark matter allowed these early galaxies to grow much larger and more quickly than they would have without its presence. As galaxies evolved, dark matter continued to influence their structure and behavior. The dark matter halo surrounding a galaxy extends far beyond the visible disk of stars, creating an extended gravitational field. This field helps to stabilize the galaxy's rotation and shape, preventing stars from flying off into space. Dark matter also plays a crucial role in galaxy collisions and mergers, affecting how galaxies interact and combine over cosmic time. Furthermore, dark matter influences the distribution of galaxies on a larger scale. It forms a cosmic web of filaments and nodes, guiding the formation of galaxy clusters and superclusters. This large-scale structure, shaped by dark matter, has a profound impact on the ongoing evolution of galaxies. determining their environments and the resources available for continued growth and star formation. Dark matter and cosmic voids share a fascinating relationship in the structure of our universe. Cosmic voids are vast regions of space that contain very few galaxies, while dark matter is the invisible substance that makes up about 85% of all matter in the universe. These two components of the cosmos interact in ways that shape the very fabric of space. Dark matter plays a crucial role in the formation and evolution of cosmic voids. As the universe expanded after the Big Bang, areas with slightly more dark matter attracted additional matter through gravity, eventually forming galaxies and galaxy clusters. Meanwhile, regions with less dark matter became increasingly empty, developing into the cosmic voids we observe today. The boundaries of cosmic voids are particularly interesting. Here, we find filaments and walls of galaxies that trace the invisible web of dark matter stretching across the universe. These structures form a cosmic scaffold with voids nestled between the dark matter filaments. This arrangement creates a foam-like structure on the largest scales of the universe, with cosmic voids representing the empty spaces within this cosmic foam. Studying the relationship between dark matter and cosmic voids helps scientists better understand the distribution of matter in the universe and test theories of gravity and cosmic evolution. By mapping the locations and sizes of voids, researchers can infer the properties of dark matter and gain insights into the fundamental forces shaping our cosmos. Our understanding of dark matter significantly influences models of cosmic flatness. Dark matter, an invisible form of matter that does not interact with light, plays a crucial role in shaping the large-scale structure of the universe. Its gravitational effects are essential for explaining the observed distribution of galaxies and the rotation curves of spiral galaxies. When considering cosmic flatness, dark matter becomes a key component in the overall mass-energy budget of the universe. Observations suggest that the universe is remarkably close to being flat, meaning that its geometry on the largest scales is Euclidean. This flatness requires a precise balance between the expansion rate of the universe and its total energy density. Dark matter contributes substantially to this energy density, accounting for approximately 5 times more mass than ordinary visible matter. By including dark matter in our models, cosmologists can better reconcile the observed flatness of the universe with other measurements, such as the cosmic microwave background radiation and the large-scale distribution of galaxies. Furthermore, dark matter helps explain how structure formed in the early universe. Its gravitational influence allowed matter to clump together more effectively, forming the cosmic web of galaxies and galaxy clusters we observe today. This structure formation process is intimately linked to the overall geometry and evolution of the universe, making dark matter an essential element in our understanding of cosmic flatness and the universe's large-scale properties. The large-scale structure of the universe refers to the vast cosmic web that forms the backbone of our cosmos. On the grandest scales, matter is not distributed uniformly throughout space. Instead, it forms an intricate pattern resembling a cosmic web with dense clusters of galaxies connected by long filaments of gas and dark matter. These filaments stretch across hundreds of millions of light years, creating a network that spans the observable universe. Between these structures lie enormous cosmic voids, regions of space that are nearly empty of galaxies and visible matter. These voids can span tens or even hundreds of millions of light years in diameter. The arrangement of this cosmic web is thought to have originated from tiny fluctuations in the density of matter in the early universe. Over billions of years, gravity has amplified these initial variations, drawing matter together into the complex structure we observe today. This process has been largely driven by dark matter, which interacts only through gravity and forms the scaffolding upon which visible matter accumulates. Understanding the large-scale structure provides crucial insights into the history and evolution of the universe. It offers clues about the distribution of dark matter, the nature of dark energy, and the processes that have shaped our cosmos since the Big Bang. By mapping and studying this cosmic web, scientists continue to refine our understanding of the fundamental laws that govern our universe. Galaxies don't exist in isolation. They are drawn together by the inexorable pull of gravity, forming vast cosmic structures that stretch across the universe. These galactic congregations begin with small groups of galaxies, often containing just a few members. Over time, these groups merge and combine, growing into larger assemblages known as galaxy clusters. Galaxy clusters are enormous collections of hundreds or even thousands of galaxies, all bound together by their mutual gravitational attraction. These clusters can span millions of light-years across, dwarfing the size of individual galaxies. But the story of cosmic structure doesn't end there. Galaxy clusters themselves are part of even larger formations. These immense structures, called superclusters, are among the largest known objects in the universe. Superclusters comprise multiple galaxy clusters and groups, along with vast regions of intergalactic space. They form intricate patterns across the cosmos, creating a cosmic web of filaments and voids that stretches across billions of light-years. This cosmic web reveals the underlying structure of the universe on its grandest scales. Galaxies and clusters tend to be found along the filaments of this web, while the spaces between these filaments are largely empty voids. This pattern is thought to have its origins in the earliest moments of the universe, with tiny fluctuations in the density of matter growing over billions of years into the enormous structures we see today. Cosmic voids are vast regions of space that contain very few or no galaxies. These enormous empty areas stretch across millions of light-years, forming an integral part of the cosmic web that makes up the large-scale structure of the universe. Imagine a giant cosmic sponge, where the holes represent the voids and the solid parts represent clusters and filaments of galaxies. These cosmic voids are not completely empty, as they still contain dark matter and a sparse distribution of gas. However, compared to the dense clusters and filaments that surround them, voids appear as barren cosmic deserts. They form as a result of the expansion of the universe and the gravitational pull of matter, which causes galaxies to clump together, leaving behind these enormous empty spaces. In the context of large-scale structure, cosmic voids play a crucial role in shaping the distribution of matter throughout the universe. They act as negative space, defining the boundaries of galaxy clusters and the cosmic web. By studying these voids, scientists can gain insights into the expansion of the universe, the nature of dark energy, and the processes that govern galaxy formation and evolution. Interestingly, the edges of cosmic voids are areas of great scientific interest. These boundaries, where voids meet clusters and filaments, are thought to be prime locations for the formation of new galaxies. As such, cosmic voids are not just empty spaces, but dynamic regions that influence the ongoing evolution of the universe. Filaments and walls of galaxies are vast structures that form the cosmic web, shaping the large-scale structure of our universe. These immense formations emerge from the interplay of gravity and the expansion of space over billions of years. The process begins in the early universe, where tiny fluctuations in the density of matter originating from quantum effects are amplified by cosmic inflation. As the universe expands and cools, these slight variations in density grow under the influence of gravity. Regions with slightly more matter attract additional material, while less dense areas become more depleted. Over time, this gravitational attraction causes matter to flow along paths of least resistance, forming a network of interconnected streams. These streams of matter eventually coalesce into the filaments and walls we observe today. Filaments are long, thread-like structures that can span hundreds of millions of light-years, while walls are flatter, sheet-like formations that can extend even further. Galaxies form within these filaments and walls, clustering together in groups and clusters. The areas between these structures, known as cosmic voids, become increasingly empty as matter is drawn away. This ongoing process of structure formation continues to shape our universe, with filaments and walls serving as the scaffolding upon which galaxies and clusters are built. The largest known structure in the universe is the Hercules Corona Borealis Great Wall. This colossal cosmic structure stretches across an incredible distance of approximately 10 billion light-years. To put this into perspective, it would take light, traveling at 300,000 kilometers per second, 10 billion years to traverse this immense structure from one end to the other. The Hercules Corona Borealis Great Wall is a vast supercluster of galaxies consisting of numerous galaxy clusters and groups interconnected by filaments of gas and dark matter. This structure was discovered through observations of gamma-ray bursts, which are incredibly energetic explosions that occur when massive stars collapse or when neutron stars collide. What makes the Hercules Corona Borealis Great Wall particularly fascinating is its sheer scale. It challenges our understanding of the universe's structure and formation. According to our current models of cosmic evolution, structures of this size should not exist, as they would have required more time to form than the age of the universe itself. This discovery has led scientists to question and refine their theories about the early universe and the processes that shape the cosmic web we observe today. The existence of such enormous structures continues to push the boundaries of our knowledge and inspires further exploration of the cosmos. The observed large-scale structure of the universe provides compelling evidence that supports the flat universe model. Astronomers have mapped out vast cosmic structures, including galaxy clusters, superclusters, and enormous voids, using advanced telescopes and surveys. These observations reveal a pattern of matter distribution that aligns closely with predictions made by the flat universe model. One key piece of evidence comes from the cosmic microwave background radiation, which shows tiny temperature fluctuations across the sky. These fluctuations correspond to density variations in the early universe that eventually led to the formation of large-scale structures we see today. The size and distribution of these fluctuations match what we would expect in a flat universe. Furthermore, the way galaxies cluster together on large scales follows a pattern consistent with a flat geometry. In a flat universe, we expect to see a specific statistical distribution of galaxy clusters, and observations from large-scale galaxy surveys align remarkably well with these predictions. This agreement between theory and observation provides strong support for the flat universe model. However, it's important to note that while the observed large-scale structure strongly favors a flat universe, it doesn't completely rule out alternative models. Scientists continue to refine their observations and theories, always open to new evidence that might challenge or modify our current understanding of cosmic geometry. Gravity is the fundamental force that shapes the large-scale structure of the universe. It acts as the cosmic architect, orchestrating the formation and evolution of galaxies, galaxy clusters, and the vast cosmic web that spans the observable universe. On the grandest scales, gravity causes matter to clump together, forming dense regions that eventually become the building blocks of cosmic structures. This process began in the early universe, when tiny fluctuations in the distribution of matter, amplified by gravity, grew into larger and larger structures over billions of years. Gravity's influence can be seen in the filamentary structure of the cosmic web, where galaxies and galaxy clusters are arranged along vast threads and sheets separated by enormous voids. These filaments act as cosmic highways, guiding the flow of matter and energy across immense distances. At the same time, gravity works to hold cosmic structures together. It keeps stars bound within galaxies, galaxies clustered together, and even governs the dance of galaxy clusters as they move through space. Without gravity, the universe would be a formless expanse of diffuse matter, devoid of the rich tapestry of structures we observe today. Computer simulations have become an indispensable tool in our quest to understand the formation of cosmic structures. These powerful digital models allow scientists to recreate the evolution of the universe from its earliest moments to the present day, offering insights that would be impossible to gain through observation alone. By inputting known physical laws and initial conditions based on our observations of the early universe, researchers can run simulations that span billions of years in just a matter of days or weeks. These simulations track the behavior of dark matter, gas, and other components as they interact under the influence of gravity and other forces. The results often reveal complex patterns of structure formation, from the filamentary cosmic web to the formation of galaxies and galaxy clusters. One of the key advantages of computer simulations is their ability to test different theories and scenarios. Scientists can adjust parameters, such as the amount of dark matter or the strength of cosmic expansion, to see how these changes affect the resulting structures. This allows them to compare the simulated universes with our observed universe, helping to refine our understanding of cosmic evolution and the fundamental properties of our universe. Moreover, simulations can provide predictions for future observations, guiding astronomers in their search for specific cosmic phenomena. They have been instrumental in our understanding of galaxy mergers, the distribution of dark matter, and the formation of the largest structures in the universe. As computing power continues to increase, these simulations become ever more detailed and accurate, bringing us closer to a comprehensive understanding of our cosmic history. The topology of the universe refers to its overall shape and structure on the largest scales. It describes how space is connected and whether it has any boundaries or unusual geometric properties. Cosmologists study topology to understand the fundamental nature of our universe and how it might behave on scales far beyond what we can directly observe. When we talk about the topology of the universe, we are essentially asking questions about its global geometry. Is the universe finite or infinite? Does it have a flat, spherical, or hyperbolic geometry? Are there any strange connections or loops in space that could allow light to travel in peculiar paths? One intriguing possibility is that the universe might have a complex topology similar to a three-dimensional donut or a more exotic shape. In such a scenario, traveling in one direction for a very long time could potentially bring you back to your starting point, much like how traveling around the Earth eventually leads you back to where you began. Understanding the topology of the universe has profound implications for our understanding of cosmic evolution, the fate of the universe, and even the nature of reality itself. It challenges our intuitions about space and pushes the boundaries of what we consider possible in the cosmos. Topology and geometry offer distinct yet complementary approaches to understanding the structure of our universe. Geometry focuses on the precise measurements, shapes, and angles of space, providing a detailed picture of the local features we observe. It deals with concepts like the curvature of space-time and the specific dimensions of cosmic structures. Topology, on the other hand, takes a broader view. It examines the overall shape and connectivity of the universe, regardless of exact measurements or local details. Topological studies consider questions about the global structure of space, such as whether the universe is finite or infinite, and whether it connects back on itself in ways that might not be immediately apparent from our limited vantage point. While geometry might tell us about the curvature of space around a massive object like a black hole, topology would be concerned with whether our universe has handles or holes on a cosmic scale. These large-scale features could have profound implications for the way light and matter move through the cosmos, potentially creating unusual patterns or connections that geometry alone might not predict. The interplay between topology and geometry becomes crucial when scientists attempt to model the universe as a whole. Topological considerations can inform theories about the origin and evolution of the cosmos, offering insights into fundamental questions about the nature of space and time that go beyond what geometry alone can provide. Cosmologists have proposed several intriguing topological models for a flat universe, each offering a unique perspective on the structure of our cosmos. One possibility is the infinite Euclidean space, where the universe extends without bounds in all directions. This model aligns with our everyday experience of space and is often the default assumption in cosmological calculations. Another fascinating option is the three-torus model, also known as the donut universe. In this scenario, the universe is finite but has no boundaries. If you were to travel far enough in any direction, you would eventually return to your starting point, much like circumnavigating a globe. However, unlike a sphere, this would happen in all three spatial dimensions. The Klein bottle universe presents an even more mind-bending concept. This model suggests a universe that is not only finite and boundaryless, but also non-orientable. Imagine a two-dimensional being living on the surface of a Klein bottle. They could traverse the entire universe and return to their starting point with their left and right sides reversed. These topological models challenge our intuitions about space and highlight the complex possibilities for the structure of our universe. While current observations favor a flat geometry, the exact topology remains an open question in cosmology, inviting further exploration and study. The concept of a finite universe without boundaries might seem counterintuitive, but it is indeed possible according to some cosmological models. This idea is often compared to the surface of a sphere, which is finite in area but has no edge or boundary. Imagine ants walking on the surface of a balloon. They can travel in any direction indefinitely without ever reaching an edge, yet the surface area they explore is finite. In the context of our three-dimensional universe, this concept becomes more complex. One possibility is that our universe could be curved in a higher dimension, similar to how a two-dimensional surface can curve in three-dimensional space. This curvature could allow the universe to wrap around on itself, creating a finite volume without any boundaries. Another model suggests that the universe might have a complex topology, like a three-dimensional analog of a torus or a more intricate shape. In such a universe, traveling in one direction long enough would eventually bring you back to your starting point, much like circumnavigating the Earth. These models of a finite, boundaryless universe are not just mathematical curiosities. They have implications for our observations of the cosmos, potentially affecting the distribution of matter on large scales and the patterns we see in the cosmic microwave background radiation. While current observations favor a flat, possibly infinite universe, the possibility of a finite universe without boundaries remains an intriguing concept in cosmology. A multiply-connected universe refers to a fascinating concept in cosmology where space has a complex topological structure. In this scenario, the universe is not simply a vast expanse stretching out in all directions. Instead, it possesses connections or shortcuts between seemingly distant regions. Imagine a sheet of paper. Normally, to get from one edge to the other, you would need to travel across the entire surface. However, if you roll that paper into a cylinder and connect the edges, you create a shortcut. You could now move from one edge to the other by going through the cylinder. This simple analogy helps illustrate the idea of a multiply-connected universe, albeit in a much more complex, three-dimensional form. In a multiply-connected universe, light and matter could potentially travel along these cosmic shortcuts, creating intriguing effects. For instance, we might see multiple images of the same galaxy in different parts of the sky, or observe light that has traveled around the entire universe more than once. These connections could also influence the overall shape and behavior of the cosmos in ways that challenge our current understanding of space and time. While the concept of a multiply-connected universe remains theoretical, it continues to captivate cosmologists and astrophysicists. They are actively searching for observational evidence that might support or refute this intriguing possibility, pushing the boundaries of our knowledge about the fundamental nature of our universe. To detect unusual topology in our universe, scientists employ several ingenious methods. One approach involves searching for repeating patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. If our universe had a finite size or unusual shape, we might observe the same patterns appearing multiple times in different directions, like seeing repeated reflections in a hall of mirrors. Another technique examines the distribution of galaxies and galaxy clusters on the largest scales. In a universe with non-standard topology, we might find unexpected arrangements or correlations in the positions of these cosmic structures. Astronomers use powerful telescopes and sophisticated computer simulations to map and analyze these distributions, looking for telltale signs of unusual geometry. Gravitational waves offer yet another avenue for exploration. As these ripples in space-time travel across the cosmos, they could be affected by the overall shape and connectivity of space. By studying the properties of gravitational waves from various sources, scientists hope to uncover clues about the universe's underlying structure. Advances in cosmological theory and observational technology continue to refine our ability to probe the universe's shape. While current evidence suggests our universe is flat and potentially infinite, the quest to understand its true topology remains an active and exciting area of research, pushing the boundaries of our cosmic understanding. To uncover the true topology of the universe, scientists rely on several key observational methods. One crucial approach involves studying the cosmic microwave background radiation, the oldest light in the universe. By analyzing patterns in this radiation, cosmologists can search for repeating structures or unusual alignments that might indicate a finite or curved universe. Another important line of evidence comes from examining the distribution of galaxies on the largest scales. If the universe has a non-trivial topology, we might observe repeating patterns in the arrangement of galaxy clusters across vast distances. This could manifest as a kind of cosmic hall of mirrors, where the same structures appear to repeat in different directions or at different distances. Gravitational lensing offers yet another tool for probing cosmic topology. As light from distant galaxies bends around massive objects, it can create multiple images of the same source. In a universe with unusual topology, we might observe unexpected patterns or correlations in these lensed images that could reveal the underlying shape of space. Precise measurements of the universe's curvature also play a crucial role. By carefully mapping the geometry of space on the largest observable scales, scientists can determine whether the universe is flat, positively curved like a sphere, or negatively curved like a saddle. This information, combined with other observational data, helps constrain possible topological models and brings us closer to understanding the true shape of our cosmic home. Cosmic topology and multiverse theory are interconnected ideas that explore the fundamental nature and structure of our universe. Cosmic topology examines the overall shape and connectivity of space, investigating whether our universe is finite or infinite, flat or curved. This concept becomes particularly intriguing when we consider the possibility of multiple universes. The multiverse theory suggests that our universe might be just one of many universes, each with its own unique properties and physical laws. Some versions of this theory propose that these universes could have different topological structures. For instance, while our observable universe appears to be flat and potentially infinite, other universes within the multiverse might have more exotic topologies, such as being curved or having unusual connectivity. One fascinating implication of cosmic topology in relation to the multiverse is the idea of cosmic connectivity. Some theories propose that certain topological configurations could allow for connections between different universes. These hypothetical links, sometimes called wormholes or Einstein-Rosen bridges, could potentially connect distant parts of our universe or even bridge gaps between separate universes within the multiverse. The study of cosmic topology in the context of multiverse theory also raises questions about the origins of our universe. Some models suggest that universes with certain topological properties might be more likely to form or sustain life, leading to anthropic considerations in our understanding of why our universe has the specific shape and structure we observe. This interplay between cosmic topology and multiverse theory continues to drive research and spark imagination in the field of cosmology. The horizon problem is a fundamental challenge in our understanding of the early universe. It arises from the observation that distant regions of space, which should have never been in contact with each other, appear to have the same temperature and other physical properties. This uniformity is puzzling because these regions are so far apart that light or any other form of information could not have traveled between them since the beginning of the universe. To grasp the scale of this issue, imagine looking at opposite sides of the observable universe. These areas are so distant from each other that light from one side has not had enough time to reach the other side, even after billions of years. Yet, when we observe the cosmic microwave background radiation, which is the afterglow of the Big Bang, we see that the temperature is nearly identical in all directions, varying by only tiny fractions of a degree. This consistency across vast cosmic distances raises a crucial question. How did these regions come to be so similar if they were never in causal contact? The horizon problem challenges our understanding of the early universe and the mechanisms that could have produced such uniformity on a cosmic scale. The most widely accepted solution to the horizon problem is the theory of cosmic inflation. This theory proposes that the early universe underwent a brief period of exponential expansion, which would have allowed initially connected regions to stretch far apart, explaining the observed uniformity. However, the exact details of inflation and its underlying mechanisms remain active areas of research in cosmology. The horizon problem and the observed flatness of the universe are two separate but related puzzles in cosmology that both find their resolution in the theory of cosmic inflation. The horizon problem arises from the observation that distant regions of the universe, which should never have been in causal contact given the age and expansion rate of the universe, appear remarkably similar in temperature and other properties. This uniformity is difficult to explain without a mechanism for these regions to have interacted in the past. The flatness problem, on the other hand, refers to the fact that the universe appears to be extremely close to flat on large scales. This means that the density of matter and energy in the universe is very close to the critical density required for a flat geometry. Such precise balance is highly improbable without a physical explanation. Cosmic inflation provides a solution to both these problems. It proposes that the early universe underwent a brief period of exponential expansion, stretching a tiny, causally connected region to cosmic scales. This expansion would have smoothed out any initial curvature, explaining the observed flatness. Simultaneously, it would have allowed initially connected regions to expand beyond each other's horizons, resolving the horizon problem. Thus, while the horizon problem and the flatness of the universe are distinct observations, they are linked by their common solution in inflationary theory, highlighting the interconnected nature of cosmic phenomena and the power of unified explanations in cosmology. The uniformity of the cosmic microwave background radiation across vast distances presents a profound puzzle in cosmology. This ancient light, originating from the early universe about 380,000 years after the Big Bang, appears remarkably consistent in all directions we observe. The problem arises when we consider the size of the observable universe and the speed of light. Regions on opposite sides of the sky are so far apart that light, or any form of information, could not have traveled between them in the time since the Big Bang. Yet, these distant regions show nearly identical temperatures and properties in the cosmic microwave background. This uniformity suggests that these far-flung areas of the cosmos were once in causal contact, able to exchange information and reach a state of equilibrium. However, the vast distances involved make this seemingly impossible within the standard model of cosmology. This conundrum, known as the horizon problem, challenges our understanding of the early universe and has led cosmologists to propose theories like cosmic inflation to explain this puzzling uniformity. The search for a complete explanation continues to drive research in modern cosmology, pushing the boundaries of our knowledge about the universe's earliest moments. Inflation theory elegantly solves the horizon problem by proposing a brief period of exponential expansion in the early universe. This rapid growth occurred just fractions of a second after the Big Bang, causing the universe to expand faster than the speed of light. During this inflationary epoch, regions that were once in close contact and able to share information were stretched far apart, beyond what would be possible with standard expansion. The horizon problem arises from the observation that distant regions of the universe appear remarkably similar in temperature and other properties, despite seemingly never having been in causal contact. Inflation explains this uniformity by suggesting that these regions were actually in close proximity and able to interact before the inflationary period began. As the universe underwent this rapid expansion, quantum fluctuations were amplified to cosmic scales, providing the seeds for structure formation. These tiny variations in density eventually led to the formation of galaxies and large-scale structures we observe today. Inflation theory thus not only addresses the horizon problem, but also provides a mechanism for the origin of cosmic structure. By drastically increasing the size of the observable universe, inflation also explains why the cosmos appears so flat and homogeneous on large scales. This theory has become a cornerstone of modern cosmology, offering solutions to multiple cosmological puzzles while making predictions that have been supported by subsequent observations. The horizon problem in cosmology has puzzled scientists for decades, leading to several alternative explanations beyond the widely accepted theory of cosmic inflation. One intriguing possibility is the variable speed of light hypothesis. This idea suggests that the speed of light might have been much faster in the early universe, allowing distant regions to be in causal contact despite the vast distances between them today. Another proposed solution is the ekpyrotic universe model. This concept envisions our universe as part of a higher dimensional space, with our three-dimensional world existing on a membrane or brane. In this scenario, the uniformity we observe could be the result of a collision between two such branes, spreading uniformity across the cosmos without the need for inflation. Some researchers have explored the idea of a cyclical universe, where our observable universe goes through repeated cycles of expansion and contraction. In this model, the uniformity we see could be a remnant of a previous cycle, preserved through the bouncing process. This explanation challenges the notion of a single Big Bang origin for our universe. There are also more exotic proposals, such as varying fundamental constants or alternative gravity theories, which attempt to resolve the horizon problem by modifying our understanding of basic physical laws. While these ideas remain speculative, they demonstrate the ongoing efforts of cosmologists to explore all possible explanations for the puzzling features of our universe. The horizon problem poses a significant challenge to our understanding of the early universe, particularly in relation to causality. This cosmological puzzle arises from observations of the cosmic microwave background radiation, which shows remarkable uniformity across vast distances in the sky. The issue lies in the fact that regions of space separated by enormous distances appear to have nearly identical temperatures and other properties. However, according to our current understanding of the speed of light and the age of the universe, these regions should never have been in causal contact with each other. In other words, there hasn't been enough time since the Big Bang for light or any other form of information to travel between these distant areas. This uniformity suggests that these regions must have been in thermal equilibrium at some point in the past, which seems to violate the principle that nothing can travel faster than light. The horizon problem thus challenges our understanding of how the universe could have achieved such uniformity without violating the laws of physics as we know them. One proposed solution to the horizon problem is the theory of cosmic inflation, which suggests that the universe underwent a period of rapid exponential expansion in its earliest moments. This expansion would have allowed regions that were once in causal contact to be stretched far apart, explaining the observed uniformity. However, while inflation provides a potential answer, it also raises new questions about the nature of the universe and the forces that drove this explosive growth. The horizon problem in cosmology arises from the observation that distant regions of the universe appear remarkably similar, despite seemingly having no way to communicate or reach thermal equilibrium. This puzzle has led scientists to propose various solutions, with the most widely accepted being cosmic inflation. Observational evidence supporting the inflationary model comes from several sources. The cosmic microwave background radiation, first detected by Arno Penzias and Robert Wilson in 1964, provides crucial support. This ancient light shows an incredibly uniform temperature across the entire sky, with tiny fluctuations that match predictions made by inflationary theory. The Planck satellite and other missions have mapped these fluctuations with unprecedented precision, further bolstering the case for inflation. Another piece of evidence comes from the distribution of galaxies in the universe. The theory of inflation predicts a specific pattern of galaxy clustering on large scales, which has been observed in extensive galaxy surveys like the Sloan Digital Sky Survey. These observations reveal a cosmic web structure that aligns closely with inflationary models. While inflation remains the leading explanation for the horizon problem, some scientists continue to explore alternative solutions. These include varying speed of light theories and cyclic universe models. However, these alternatives currently lack the same level of observational support as inflation, and many struggle to explain the full range of cosmological observations as comprehensively as the inflationary paradigm does. The horizon problem and cosmic flatness are two interconnected aspects of our universe that have puzzled cosmologists for decades. Solving the horizon problem has provided crucial insights into the early universe, which in turn helps explain the observed flatness of space. The horizon problem arises from the fact that distant regions of the observable universe appear to have the same temperature and other properties, despite never having been in causal contact according to the standard Big Bang model. This uniformity is difficult to explain without a mechanism for these regions to have interacted in the past. Cosmic inflation, a theory proposed to solve the horizon problem, suggests that the early universe underwent a brief period of exponential expansion. This rapid growth would have allowed previously connected regions to expand far beyond their original horizons, explaining the observed uniformity. Importantly, this same inflationary period also provides a solution to the flatness problem. The flatness problem refers to the observation that the universe appears to be extremely close to flat, meaning that its overall geometry is Euclidean. Inflation naturally drives the universe towards flatness by stretching space so dramatically that any initial curvature would be smoothed out, much like inflating a balloon makes its surface appear increasingly flat. Thus, by addressing the horizon problem, inflation simultaneously offers an explanation for the observed flatness of the universe, demonstrating the interconnected nature of these cosmic puzzles and deepening our understanding of the early universe. Quantum fluctuations are tiny, temporary changes in energy that happen at the smallest scales of the universe. These fluctuations are a fundamental aspect of quantum mechanics, the branch of physics that describes the behavior of matter and energy at the atomic and subatomic levels. At the quantum scale, the universe is not static, but constantly buzzing with activity. Even in seemingly empty space, pairs of particles and antiparticles spontaneously appear and disappear in an instant. These fleeting particle pairs are a manifestation of quantum fluctuations, emerging from the inherent uncertainty that exists at these minuscule scales. The occurrence of quantum fluctuations is rooted in the Heisenberg uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. This principle allows for brief violations of energy conservation, permitting particles to pop into existence for extremely short periods. These quantum fluctuations play a crucial role in many aspects of the universe. They contribute to the quantum foam that makes up the fabric of spacetime, influence the behavior of virtual particles, and may have even seeded the initial density variations that led to the formation of galaxies and large-scale structures in the cosmos. Understanding quantum fluctuations is essential for grasping the fundamental nature of reality at its most basic level. Quantum fluctuations in the early universe played a crucial role in shaping the cosmic structure we observe today. These tiny, random variations in energy and density emerged during the first fractions of a second after the Big Bang, when the universe was incredibly hot and dense. As the universe expanded and cooled, these quantum fluctuations were stretched to cosmic scales. Regions with slightly higher density began to attract more matter through gravity, while less dense areas became more empty. This process of gravitational attraction and cosmic expansion amplified the initial quantum fluctuations, leading to the formation of the first stars and galaxies. Over billions of years, these small irregularities evolved into the vast cosmic web we see today, with galaxy clusters, filaments, and voids. The largest structures in the universe, such as superclusters of galaxies, can be traced back to these primordial quantum fluctuations. Remarkably, we can observe evidence of these ancient quantum fluctuations in the cosmic microwave background radiation, the oldest light in the universe. The slight temperature variations in this radiation correspond to the density fluctuations that seeded cosmic structure, providing a direct link between the quantum world and the large-scale universe we inhabit. Quantum fluctuations are crucial to our understanding of cosmic inflation, the theory that describes the rapid expansion of the universe in its earliest moments. These tiny, unpredictable variations in energy at the quantum scale serve as the seeds for all the structure we see in the cosmos today. During the inflationary period, which occurred just a fraction of a second after the Big Bang, the universe expanded at an incredible rate. This expansion stretched quantum fluctuations from the subatomic scale to cosmic proportions. As inflation ended, these fluctuations became locked in place as slight differences in the density of matter across space. These density variations, originating from quantum fluctuations, provided the initial conditions for the formation of galaxies, stars, and planets. In regions where matter was slightly denser, gravity could begin to pull material together, eventually leading to the cosmic web of structure we observe today. The imprint of these primordial quantum fluctuations can still be seen in the cosmic microwave background radiation, the oldest light in the universe. The slight temperature variations in this radiation map directly to the density fluctuations caused by quantum effects during inflation, providing strong evidence for this remarkable connection between the quantum world and the large-scale structure of the cosmos. Quantum fluctuations, those tiny ripples in the fabric of space-time, left an indelible mark on the cosmic microwave background radiation. This ancient light, which has traveled across the universe for nearly 14 billion years, carries within it the echoes of these primordial disturbances. When we observe the cosmic microwave background, we see subtle temperature variations. These variations, mere fractions of a degree, are the direct result of quantum fluctuations that occurred in the earliest moments of the universe. As the universe expanded rapidly during inflation, these quantum scale variations were stretched to cosmic proportions, becoming the seeds of all structure we see today. The pattern of these temperature fluctuations in the cosmic microwave background is not random. It follows a specific statistical distribution that aligns perfectly with what we would expect from quantum mechanics. This remarkable consistency between theory and observation provides strong evidence for the quantum origin of cosmic structure. By studying these minute temperature differences in the cosmic microwave background, scientists can peer back to a time when the universe was just 380,000 years old. This allows us to test theories about the very early universe and the nature of quantum mechanics on a cosmic scale, bridging the gap between the infinitesimally small and the unimaginably large. Yes, we can indeed observe the effects of primordial quantum fluctuations in the current universe. These tiny ripples in the fabric of space-time, which originated in the earliest moments after the Big Bang, have left an indelible mark on the cosmos we see today. The most striking evidence of these ancient quantum fluctuations is found in the cosmic microwave background radiation. This faint glow, permeating all of space, is the oldest light in the universe, dating back to about 380,000 years after the Big Bang. When we study this radiation, we discover minute temperature variations across the sky, typically differing by only a few millionths of a degree. These subtle differences are the direct result of those primordial quantum fluctuations now expanded to cosmic scales. These initial fluctuations also played a crucial role in shaping the large-scale structure of the universe. As the cosmos expanded and matter began to clump together under the influence of gravity, these tiny variations served as the seeds for the formation of galaxies and galaxy clusters. The web-like structure of the universe, with its vast voids and dense filaments of galaxies, can be traced back to these quantum-scale irregularities. Modern cosmological simulations have demonstrated that the observed distribution of matter in the universe aligns remarkably well with predictions based on these primordial fluctuations. This agreement between theory and observation provides strong support for our understanding of the quantum origins of cosmic structure, linking the subatomic world to the grandest scales of the universe. Quantum fluctuations play a crucial role in the formation of galaxies and clusters, acting as the initial seeds for cosmic structure. These minute variations in energy and matter occurring at the subatomic level were present in the earliest moments of the universe. During the period of cosmic inflation, which took place just fractions of a second after the Big Bang, these quantum fluctuations were stretched to cosmic scales. As the universe expanded rapidly, these tiny irregularities grew into larger density variations across space. These density variations became the foundation for the cosmic web we observe today. In regions where matter was slightly more concentrated, gravity began to pull in surrounding material, gradually forming the first stars and galaxies. Over billions of years, these initial structures merged and grew, eventually giving rise to the massive galaxy clusters we see in the present-day universe. The process demonstrates how phenomena at the smallest scales can have profound effects on the largest structures in the cosmos. Quantum fluctuations, amplified by inflation and shaped by gravity over cosmic timescales, ultimately led to the rich, diverse universe we inhabit today. Quantum fluctuations and cosmic flatness are two fundamental concepts in our understanding of the universe, linked through the theory of cosmic inflation. Quantum fluctuations, tiny variations in energy and matter at the subatomic level, played a crucial role in shaping the early universe. These microscopic variations were dramatically amplified during the period of rapid expansion known as cosmic inflation. Cosmic flatness refers to the overall geometry of the universe, which observations suggest is remarkably close to being perfectly flat. This flatness is a consequence of cosmic inflation, which stretched the fabric of spacetime to an enormous degree in the first fraction of a second after the Big Bang. As the universe expanded exponentially, any initial curvature was smoothed out, much like inflating a balloon makes its surface appear flatter. The quantum fluctuations that existed before inflation became the seeds for all cosmic structure we see today. As the universe expanded, these tiny variations in energy density were stretched to cosmic scales, eventually leading to the formation of galaxies, stars, and planets. The uniformity we observe in the cosmic microwave background, radiation, is a direct result of these quantum fluctuations being spread out across the inflating universe. The connection between quantum fluctuations and cosmic flatness highlights the interplay between the very small and the very large in cosmology. It demonstrates how processes at the quantum scale can have profound effects on the structure and geometry of the entire observable universe, linking the microscopic world of particle physics with the macroscopic realm of cosmology. Quantum fluctuations provide a crucial window into the earliest moments of our universe. These tiny, unpredictable variations in energy at the subatomic level are thought to be the seeds from which all cosmic structure grew. By studying quantum fluctuations, scientists can trace the origins of galaxies, stars, and even our own planet back to the first fractions of a second after the Big Bang. In the incredibly hot and dense conditions of the early universe, quantum fluctuations were amplified by a process called cosmic inflation. This rapid expansion stretched these minuscule quantum ripples into macroscopic variations in the distribution of matter and energy across the cosmos. These variations eventually led to the formation of the cosmic web of galaxies and the large-scale structure we observe today. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, reveal tiny temperature fluctuations that align remarkably well with predictions based on quantum fluctuations. This agreement between theory and observation provides strong support for our current understanding of the early universe and the role of quantum mechanics in cosmic evolution. By delving deeper into quantum fluctuations, scientists hope to uncover more about the nature of the universe in its infancy, potentially shedding light on fundamental questions about the origins of space, time, and the laws of physics themselves. This research not only helps us understand our cosmic history, but also pushes the boundaries of our knowledge about the quantum world and its connection to the vast scales of the universe. Einstein's theory of general relativity fundamentally changed our understanding of the universe's structure. It describes gravity not as a force, but as a consequence of the curvature of spacetime. This revolutionary concept suggests that the shape of the universe is intricately linked to the distribution of matter and energy within it. According to general relativity, massive objects like stars and galaxies warp the fabric of spacetime around them. This warping creates what we perceive as gravity, with larger objects causing more significant distortions. On a cosmic scale, the collective effect of all matter and energy in the universe determines its overall shape and curvature. The theory allows for three possible geometries of the universe: flat, closed, or open. A flat universe would have zero curvature, like a sheet of paper. A closed universe would have positive curvature, similar to the surface of a sphere. An open universe would have negative curvature, resembling a saddle shape. Current observations strongly suggest that our universe is remarkably close to being flat, though slight deviations are still possible. Interestingly, general relativity also predicts that the universe is dynamic, capable of expanding or contracting. This prediction laid the groundwork for the discovery of the expanding universe and the development of the Big Bang theory, further reshaping our cosmic perspective. Einstein's field equations are the cornerstone of general relativity, describing how matter and energy shape the fabric of spacetime. These equations reveal that mass and energy curve the very geometry of the universe, creating what we perceive as gravity. They tell us that space and time are not fixed, but dynamic and interconnected. The field equations connect the distribution of matter and energy to the curvature of spacetime. They show that massive objects like stars and planets create dips or wells in the cosmic fabric, much like a heavy ball on a stretched rubber sheet. This warping of spacetime guides the motion of other objects, explaining orbital paths and the bending of light around massive bodies. When applied to the entire universe, Einstein's equations provide a framework for understanding cosmic geometry on the grandest scale. They allow cosmologists to model how the universe expands, contracts, or remains static, depending on its overall energy content and distribution. These equations led to the prediction of an expanding universe years before observations confirmed it. The field equations also open the door to exotic cosmic phenomena. They predict the existence of black holes, where space-time curvature becomes so extreme that nothing can escape. On the largest scales, they form the basis for our understanding of the universe's overall shape and evolution, guiding our exploration of cosmic history from the Big Bang to the present day. General relativity explains the bending of light by massive objects through its fundamental concept of curved spacetime. According to Einstein's theory, massive objects like stars and galaxies warp the fabric of space and time around them. This warping creates a kind of cosmic landscape with hills and valleys, where objects with more mass create deeper curves in spacetime. Light always travels along the shortest path between 2 points. In flat spacetime, this path is a straight line. However, in the curved spacetime near massive objects, the shortest path becomes a curved line. As light passes near a massive object, it follows this curved path, appearing to bend around the object from our perspective. This effect is similar to how a marble rolled across a stretched rubber sheet would curve its path around a heavy ball placed on the sheet. The more massive the object, the more it curves spacetime, and the more dramatically it can bend light. This phenomenon, known as gravitational lensing, has been observed and measured many times since its first confirmation during a solar eclipse in 1919. Gravitational lensing allows astronomers to observe distant galaxies and even map dark matter, which does not emit light but still curves spacetime due to its mass. By studying how light bends around massive objects, scientists continue to test and confirm the predictions of general relativity, deepening our understanding of the fundamental nature of space, time, and gravity. Spacetime curvature is a fundamental concept in Einstein's theory of general relativity. It describes how massive objects warp the fabric of space and time around them, creating what we perceive as gravity. This curvature affects the paths of light and matter, causing them to follow curved trajectories that we interpret as gravitational attraction. The concept of a flat universe relates to the overall geometry of spacetime on a cosmic scale. In a flat universe, parallel lines remain parallel indefinitely, and the rules of Euclidean geometry apply on the largest scales. This is in contrast to a curved universe, which could be either positively curved like the surface of a sphere or negatively curved like a saddle shape. Interestingly, our current observations suggest that we live in a flat universe, or one that is very close to flat. This means that on the largest scales, the curvature of spacetime averages out to zero. However, this doesn't contradict the existence of local spacetime curvature around massive objects like stars and galaxies. The flatness of the universe is closely tied to its density. If the universe contains just the right amount of matter and energy, it will be flat. This critical density represents a delicate balance between the expansion of the universe and the gravitational pull of its contents, leading to a cosmos that is neither closed nor open, but precisely flat. General relativity, Albert Einstein's groundbreaking theory of gravity, provides a framework that elegantly explains the expansion of the universe. At its core, this theory describes how matter and energy shape the fabric of spacetime, and how this warped spacetime in turn influences the motion of objects within it. In the context of cosmology, general relativity reveals that space itself can expand. This expansion is not the movement of galaxies through space, but rather the stretching of the cosmic fabric between them. The theory predicts that a universe filled with matter and energy should be dynamic, either expanding or contracting rather than remaining static. The expansion of the universe emerges from the equations of general relativity when applied to a homogeneous and isotropic cosmos. These equations, known as the Friedmann equations, describe how the scale factor of the universe changes over time. This scale factor represents the relative size of the universe, and its rate of change corresponds to the expansion rate. Crucially, general relativity connects the expansion of the universe to its content. The density and pressure of matter and energy influence the rate of expansion, leading to different possible scenarios for the universe's evolution. This relationship between content and expansion has profound implications for our understanding of cosmic history and future, from the Big Bang to the potential fate of the universe billions of years from now. General relativity has made several remarkable predictions that have been confirmed through observation and experiment. One of the most famous is the bending of light by massive objects. Einstein proposed that gravity could curve the path of light, and this was dramatically confirmed during a solar eclipse in 1919, when stars near the edge of the sun appeared to shift position. Another key prediction is the existence of gravitational waves, ripples in the fabric of spacetime caused by accelerating massive objects. These waves were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, opening up a new field of gravitational wave astronomy. General relativity also predicted the existence of black holes, regions of space where gravity is so strong that nothing, not even light, can escape. While black holes cannot be directly observed, their effects on surrounding matter and space have been extensively studied, confirming their existence. The theory also accurately accounts for Mercury's peculiar orbit, which could not be fully explained by Newtonian physics. It predicts the slowing of time in strong gravitational fields, an effect that has been measured using precise atomic clocks at different altitudes on Earth. These confirmations have solidified general relativity as one of the most successful and well-tested theories in physics. General relativity, our best description of gravity on cosmic scales, encounters significant challenges when applied to the extreme conditions of the very early universe. As we approach the first moments after the Big Bang, the theory begins to falter in several key areas. The most glaring issue arises as we near the singularity at the beginning of time. General relativity predicts infinite densities and temperatures, which are physically meaningless. These infinities signal that the theory is reaching its limits of applicability, unable to describe the universe in its earliest instance. Furthermore, general relativity does not account for quantum effects, which become increasingly important at the microscopic scales and high energies of the early universe. The theory treats space and time as smooth and continuous, but at the quantum level, this assumption breaks down. The marriage of quantum mechanics and gravity remains one of the most significant unsolved problems in physics. Another limitation emerges when considering the rapid expansion of space during the inflationary period. While general relativity can describe expansion, the extreme rate of inflation stretches the theory to its limits, requiring additional explanations beyond its framework. These challenges highlight the need for a more comprehensive theory that can unite gravity with quantum mechanics and explain the earliest moments of our universe. Scientists have explored several alternatives to general relativity in their quest to understand the universe more comprehensively. One notable alternative is modified Newtonian dynamics, or MOND, which proposes adjustments to Newtonian physics at cosmic scales rather than introducing dark matter. MOND suggests that gravity behaves differently over vast distances, potentially explaining galactic rotation curves without the need for invisible matter. Another intriguing alternative is tensor vector scalar gravity, or TVES, which builds upon MOND by incorporating relativistic effects. TVES introduces additional fields to the gravitational framework, aiming to reconcile modified gravity with phenomena like gravitational lensing and cosmic microwave background radiation. Regarding cosmic flatness, these alternative theories approach the issue from different angles. While general relativity requires the concept of dark energy to explain the observed flatness and accelerating expansion of the universe, some modified gravity theories attempt to account for these phenomena through altered gravitational behavior at large scales. For instance, theories like F of R gravity modify the Einstein field equations, potentially explaining cosmic acceleration without invoking dark energy. These approaches suggest that the apparent flatness of the universe might be a consequence of gravity behaving differently on cosmic scales rather than the result of an unknown energy component permeating space. Astronomers employ a variety of telescopes to unravel the mysteries of cosmic geometry. Radio telescopes detect long wavelengths, allowing scientists to peer through cosmic dust and observe distant galaxies and quasars. These instruments have been crucial in mapping the large-scale structure of the universe. Optical telescopes, both on Earth and in space, capture visible light from stars and galaxies. The Hubble Space Telescope has been particularly valuable, providing high-resolution images that reveal the shapes and distributions of galaxies across vast cosmic distances. Infrared telescopes, such as the James Webb Space Telescope, detect heat signatures from celestial objects. This capability allows astronomers to study the earliest galaxies and observe how the universe has evolved over billions of years, providing vital data for understanding cosmic geometry. X-ray telescopes and gamma-ray observatories round out the arsenal, detecting high-energy phenomena like black holes and supernovae. By combining data from all these instruments, scientists can construct a comprehensive picture of the universe's structure and evolution, informing our understanding of cosmic geometry on the grandest scales. Space-based observatories have revolutionized our understanding of the universe's shape by providing unparalleled views beyond Earth's atmosphere. These advanced telescopes, orbiting high above our planet, capture pristine images and data free from atmospheric distortion and light pollution. One of the most significant contributions comes from observatories that study cosmic microwave background radiation, the afterglow of the Big Bang. By mapping tiny temperature fluctuations in this ancient light, scientists have been able to measure the curvature of space itself. These precise measurements strongly suggest that the universe is flat on the largest scales, extending in all directions without overall curvature. Space telescopes also allow us to observe distant galaxies and quasars with exceptional clarity. By studying the distribution and movement of these cosmic structures, astronomers can infer the underlying geometry of space. This has led to the discovery that the universe is not only expanding but accelerating in its expansion, a finding that has profound implications for our understanding of cosmic shape and evolution. Furthermore, space-based gravitational wave detectors are being developed to detect ripples in the fabric of space-time. These instruments will provide a new way to probe the shape and structure of the universe, potentially revealing hidden dimensions or unexpected cosmic geometries that challenge our current models of space and time. Particle accelerators serve as powerful tools in cosmological research, allowing scientists to peer into the fundamental workings of the universe. These massive machines accelerate subatomic particles to incredibly high speeds and then collide them, recreating conditions similar to those present in the early moments after the Big Bang. By studying these collisions, researchers can uncover crucial information about the nature of matter, energy, and the forces that govern our cosmos. One of the primary contributions of particle accelerators to cosmology is their ability to produce and detect exotic particles that existed in the infant universe. These fleeting particles, which cannot be observed under normal conditions, provide valuable insights into the processes that shape the cosmos in its earliest stages. For instance, the discovery of the Higgs boson at the Large Hadron Collider helped confirm our understanding of how particles acquire mass, a crucial piece of the puzzle in explaining the evolution of the universe. Particle accelerators also play a vital role in investigating dark matter, one of the most perplexing mysteries in modern cosmology. While dark matter cannot be directly observed, scientists use these machines to search for potential dark matter particles or to study the properties of known particles that might interact with dark matter. This research is essential for developing a more complete picture of the universe's composition and structure. Furthermore, accelerator experiments contribute to our understanding of the matter-antimatter asymmetry observed in the universe. By recreating conditions similar to those in the early cosmos, scientists can explore why matter came to dominate over antimatter, a crucial question in explaining the universe we see today. Through these investigations, particle accelerators continue to push the boundaries of our knowledge, connecting the infinitesimally small world of particles to the vast expanses of the cosmos. Gravitational wave detectors offer a revolutionary window into the cosmos, allowing us to perceive the universe in an entirely new way. These sophisticated instruments detect ripples in the fabric of space-time caused by some of the most energetic events in the universe, such as the collision of black holes or the merging of neutron stars. By capturing these cosmic ripples, gravitational wave detectors provide unique insights into the structure and evolution of our universe. They allow scientists to observe phenomena that are otherwise invisible to traditional telescopes, revealing the hidden dance of massive objects across vast cosmic distances. This capability enables us to map out the distribution of black holes and neutron stars throughout space, offering clues about galaxy formation and the universe's overall structure. Moreover, gravitational waves carry information about the objects that created them, including their masses, spins, and distances. This data helps astronomers better understand the life cycles of stars and the processes that shape galaxies. It also provides a new way to measure cosmic distances, complementing and refining our existing methods. Perhaps most excitingly, gravitational wave detectors open up the possibility of observing the very early universe, potentially allowing us to probe the first fractions of a second after the Big Bang. This could provide unprecedented insights into the fundamental nature of space, time, and the origin of cosmic structure, pushing our understanding of the universe to new frontiers. Scientists are employing several innovative technologies to investigate cosmic flatness, pushing the boundaries of our understanding of the universe's shape. One of the most promising methods involves using advanced telescopes to measure the cosmic microwave background radiation with unprecedented precision. These telescopes, both ground-based and spaceborne, are equipped with highly sensitive detectors that can map tiny temperature fluctuations in the early universe. Another cutting-edge approach utilizes gravitational wave detectors to study the curvature of spacetime. By analyzing the patterns of gravitational waves from distant cosmic events, researchers hope to gain insights into the large-scale geometry of the universe. This technology, still in its infancy, has the potential to provide a completely new perspective on cosmic flatness. Researchers are also developing sophisticated computer simulations that model the evolution of the universe under different curvature scenarios. These simulations, run on some of the world's most powerful supercomputers, allow scientists to compare theoretical predictions with observational data, refining our understanding of cosmic flatness. Additionally, scientists are exploring the use of quantum sensors and atomic clocks in space to measure the distribution of matter in the universe with extreme accuracy. These ultra-precise instruments could potentially detect subtle variations in the fabric of spacetime, providing new clues about the overall geometry of the cosmos and helping to resolve the question of cosmic flatness. Computer simulations play a crucial role in modern cosmology, helping scientists make sense of the vast amounts of data collected from telescopes and space probes. These powerful tools allow researchers to model complex cosmic phenomena and test theories about the universe's evolution and structure. One of the primary ways simulations assist cosmologists is by creating virtual universes. Scientists input the laws of physics and initial conditions based on our current understanding, then let these digital cosmos evolve over billions of years. The resulting simulations can be compared with actual observations of the real universe, helping researchers refine their theories and identify areas that need further investigation. Simulations are particularly valuable for studying phenomena that occur over enormous timescales or in extreme conditions that cannot be replicated in laboratories. For instance, they help scientists understand how galaxies form and evolve, how dark matter influences cosmic structure, and how the universe's expansion has changed over time. By running multiple simulations with slightly different parameters, researchers can explore various scenarios and determine which ones best match observational data. Furthermore, computer simulations aid in the design and interpretation of cosmological surveys. They help scientists predict what various instruments should detect under different conditions, allowing for more effective observation strategies and data analysis techniques. This synergy between simulations and observations has become an essential part of modern cosmological research, driving our understanding of the universe to new depths. Observing the farthest reaches of the universe presents astronomers with numerous challenges. The immense distances involved mean that light from these remote regions takes billions of years to reach Earth, so we are essentially looking back in time. This ancient light is incredibly faint by the time it reaches our telescopes, requiring highly sensitive instruments and long exposure times to detect. The expansion of the universe further complicates matters. As light travels across vast cosmic distances, it gets stretched by the expanding space, shifting it towards longer, redder wavelengths. This phenomenon, known as redshift, can push the light from the most distant objects beyond the visible spectrum into infrared or even radio waves, necessitating specialized equipment for detection. Cosmic dust and gas clouds scattered throughout space pose another obstacle. These materials can absorb or scatter light from distant sources, potentially obscuring our view of the early universe. To overcome this, astronomers often use multiple wavelengths of light to piece together a more complete picture. Additionally, the sheer volume of data generated by modern telescopes presents a significant challenge. Astronomers must sift through enormous amounts of information to identify and study the most distant objects, requiring advanced computer algorithms and data processing techniques to make sense of it all. Future advancements in technology promise to revolutionize our understanding of cosmic flatness. One key area of improvement lies in satellite-based measurements. Next-generation space telescopes will offer unprecedented precision in mapping the cosmic microwave background radiation, providing clearer insights into the universe's geometry. Ground-based observatories will also play a crucial role. Large-scale survey projects using advanced telescopes will map the distribution of galaxies across vast cosmic distances with extraordinary detail. This will allow scientists to measure the universe's large-scale structure more accurately, offering valuable clues about its overall shape and curvature. Gravitational wave detectors represent another exciting frontier. As these instruments become more sensitive, they may detect primordial gravitational waves from the early universe. Such observations could provide direct evidence of cosmic inflation, a theory closely tied to the concept of flatness. Quantum sensors and atomic clocks in space might also contribute to this quest. These ultra-precise instruments could detect minute variations in space-time, potentially revealing subtle curvatures on cosmic scales that current technologies cannot discern. As these and other innovations emerge, our ability to measure and understand cosmic flatness will undoubtedly reach new heights. The anthropic principle suggests that the universe appears finely tuned for life, because if it were any different, we wouldn't be here to observe it. This concept relates to cosmic flatness in a fascinating way. Cosmic flatness refers to the idea that the universe's geometry is remarkably balanced, neither curved inward nor outward to any significant degree. The connection between these concepts lies in the precision required for our universe to exist as we know it. For the universe to be as flat as we observe, its initial conditions needed to be incredibly fine-tuned. Even a tiny deviation in the early universe's expansion rate or energy density would have resulted in a drastically different cosmos, one that likely couldn't support life. This apparent fine-tuning leads to the anthropic explanation. We observe a flat universe because only a flat universe could give rise to the conditions necessary for our existence. It's not that the universe was designed for us, but rather that we could only evolve in a universe with these specific properties. The anthropic principle and cosmic flatness thus highlight the delicate balance of cosmic parameters that allow for our existence, prompting deeper questions about the nature of our universe and our place within it. The fine-tuning of universal constants plays a crucial role in determining the shape and structure of our universe. These constants, such as the gravitational constant, the speed of light, and the strength of the electromagnetic force, work together in a delicate balance to create the conditions necessary for our universe to exist as we know it. The shape of the universe is intimately connected to its overall density, which is influenced by these finely tuned constants. If the density of the universe is precisely equal to the critical density, it results in a flat universe that extends infinitely in all directions. This flat shape is remarkably consistent with our current observations and measurements. However, even slight variations in these constants could dramatically alter the universe's shape. If the density were slightly higher, the universe would curve in on itself, creating a closed, spherical shape with finite volume. Conversely, if the density were slightly lower, the universe would curve outward, resulting in an open, saddle-like shape that extends infinitely. The fine-tuning of these constants not only affects the overall shape of the universe, but also influences its ability to form galaxies, stars, and planets. This delicate balance has led some scientists to propose the anthropic principle, suggesting that the constants are fine-tuned to allow for the existence of life and conscious observers like ourselves. The flatness of the universe has long puzzled cosmologists, and the question of observational bias is indeed an intriguing one. Our current understanding suggests that the universe is remarkably flat on large scales, but this conclusion is based on observations from our particular vantage point. It is crucial to consider that our observations are limited to the observable universe, which is just a fraction of the entire cosmos. This limitation could potentially introduce a form of observational bias. The cosmic microwave background radiation, which provides strong evidence for the flatness of space, only shows us the oldest light we can detect from our position in space and time. However, most cosmologists believe that the observed flatness is a genuine feature of the universe rather than a result of observational bias. This conclusion is supported by multiple independent lines of evidence, including the distribution of galaxies and the behavior of light over vast distances. Furthermore, the theory of cosmic inflation, which posits a period of rapid expansion in the early universe, provides a mechanism that could explain the extreme flatness we observe. While observational bias should always be considered in scientific inquiries, the consensus among experts is that the flatness of the universe is likely a fundamental characteristic rather than an artifact of our limited perspective. Nonetheless, ongoing research and future observations may provide new insights into this fascinating aspect of our cosmos. The anthropic principle offers a thought-provoking perspective on cosmic evolution, challenging traditional views while also providing support for certain aspects of our understanding. This principle suggests that the observable universe must have properties that allow for the existence of observers, namely intelligent life like ourselves. At first glance, this idea might seem to challenge our understanding of cosmic evolution by implying a purposeful design to the universe. However, it actually aligns with our current scientific knowledge when we consider the vast number of universes that might exist. In a multiverse scenario, where countless universes with different physical laws and constants exist, it becomes statistically likely that at least one universe would have the precise conditions necessary for life to emerge. The anthropic principle also supports our understanding of fine-tuning in the universe. It explains why fundamental constants, such as the strength of gravity or the mass of elementary particles, appear to be precisely calibrated for life to exist. Rather than attributing this to design, the principle suggests that we simply find ourselves in a universe where these conditions are met because it is the only type of universe where we could exist to observe it. Furthermore, the anthropic principle encourages scientists to consider the role of observers in cosmology, leading to new questions and avenues of research. It prompts us to examine the relationship between the conditions necessary for life and the overall evolution of the cosmos, potentially revealing new insights into the nature of our universe and its development over time. The anthropic principle and multiverse theory intertwine in fascinating ways, shaping our understanding of our place in the cosmos. The anthropic principle suggests that the universe appears finely tuned for life because if it were not, we would not be here to observe it. This idea takes on new significance when considered alongside the concept of a multiverse. Multiverse theory proposes that our universe is just one of many, perhaps infinite, universes. Each of these universes might have different fundamental constants and laws of physics. In this context, the anthropic principle implies that we naturally find ourselves in a universe capable of supporting life, simply because we could not exist in one that does not. This perspective potentially resolves the puzzle of our universe's apparent fine-tuning without resorting to a designer or special purpose. Instead, it suggests that in the vast array of universes, some will inevitably have the right conditions for life, and it is only natural that we find ourselves in one of these. However, this combination of ideas also raises profound questions about the nature of reality and our place within it. It challenges us to consider whether our universe is truly unique or just one of countless others, each with its own potential for life and complexity. The anthropic principle in a multiverse context invites us to ponder the limits of our observations and the true scope of existence itself. Observer selection plays a crucial role in how we interpret cosmic flatness, shaping our understanding of the universe's geometry and evolution. This concept suggests that our observations of the cosmos are inherently biased by the fact that we exist to make those observations in the first place. When we look at the universe, we find it to be remarkably flat on large scales. This flatness is so precise that it seems to require an extraordinary degree of fine-tuning in the early universe. However, observer selection offers an alternative explanation. It posits that a flat universe might be a necessary condition for the emergence of complex life capable of pondering these cosmic questions. In a universe that is significantly curved, either positively or negatively, structures like galaxies and planets might not form in a way that allows for the development of life as we know it. Therefore, the very fact that we exist to observe the universe biases us towards observing a flat cosmos. This doesn't mean that all universes must be flat, but rather that flat universes are more likely to produce observers. This perspective shifts our interpretation of cosmic flatness from a puzzling coincidence to a potential prerequisite for our existence. It encourages us to consider a broader context when evaluating cosmological observations, reminding us that our viewpoint is not necessarily representative of all possible universes or observers. The anthropic principle in cosmology has faced several significant criticisms from scientists and philosophers alike. One major critique is that it can be seen as a form of circular reasoning, essentially stating that the universe must be compatible with our existence because we exist to observe it. Critics argue this offers little explanatory power and may even hinder scientific progress by discouraging the search for deeper physical explanations. Another criticism is that the anthropic principle can be viewed as unscientific because it is not falsifiable. Since we can only observe one universe, there is no way to test whether different physical constants would indeed lead to universes incapable of supporting life. This lack of testability puts the principle at odds with the scientific method, which relies on the ability to test and potentially disprove hypotheses. Some scientists also argue that the anthropic principle relies too heavily on our current understanding of what conditions are necessary for life. Our knowledge of life and its potential forms is limited to Earth-based examples, and it is possible that life could exist under vastly different conditions than we currently imagine. This limitation could lead to an overly narrow view of what constitutes a life-supporting universe. Lastly, there are concerns that the anthropic principle can be misused to support religious or teleological arguments about the purposeful design of the universe. While not inherently a problem with the principle itself, this potential for misinterpretation has led some scientists to be cautious about invoking anthropic reasoning in cosmological discussions. The anthropic principle has the potential to significantly shape future research in cosmology by encouraging scientists to consider the role of observers in our understanding of the universe. This principle suggests that the physical laws and constants we observe must be compatible with the existence of conscious life, as we would not be here to observe them otherwise. As cosmologists delve deeper into questions about the nature of our universe, the anthropic principle might guide them to explore multiverse theories and the possibility of varying physical constants across different cosmic domains. This could lead to innovative research methods and new ways of testing hypotheses about the fundamental properties of our universe. Furthermore, the anthropic principle could inspire cosmologists to investigate the fine-tuning of physical constants and their relationship to the emergence of complexity and life. This might involve collaborations with fields such as astrobiology and complexity science, broadening the scope of cosmological research. Ultimately, the anthropic principle could encourage a more holistic approach to cosmology, one that considers not only the physical properties of the universe, but also the conditions necessary for observers to exist within it. This perspective might lead to groundbreaking discoveries about the nature of reality and our place within it. The multiverse theory proposes that our universe is not alone, but part of a vast ensemble of universes, each with its own unique properties and physical laws. This concept challenges our traditional understanding of the cosmos and suggests that what we observe might be just one of countless possible realities. Cosmic flatness refers to the overall geometry of our universe, which observations indicate is remarkably close to being perfectly flat. This flatness is so precise that it raises questions about why our universe has this specific characteristic. The multiverse theory offers a potential explanation for this cosmic flatness puzzle. In the context of the multiverse, our universe's flatness could be seen as a result of cosmic natural selection. The idea is that universes with different properties constantly form, but only those with certain characteristics, like flatness, can expand and persist long enough to develop complex structures and life. This concept is sometimes called the anthropic principle, suggesting that we observe a flat universe because it is one of the conditions necessary for our existence. The multiverse theory also connects to cosmic flatness through the idea of eternal inflation. This model proposes that the rapid expansion of space that occurred in the early universe, known as inflation, never completely stopped. Instead, it continues in some regions, constantly giving birth to new universes with varying properties, including different degrees of flatness. Our observable universe, with its precise flatness, would be just one bubble in this ever-expanding multiverse foam. The concept of multiple universes, often referred to as the multiverse, offers an intriguing perspective on our universe's observed flatness. In cosmology, a flat universe is one where the geometry of space is not curved, and our measurements strongly suggest that our universe is indeed remarkably flat. This flatness poses a puzzle because it requires extremely precise initial conditions, which seem improbable without some explanation. The multiverse theory proposes that our universe is just one of many, perhaps even an infinite number, of universes. Each of these universes could have different physical laws, constants, and initial conditions. In this vast ensemble of universes, it becomes more likely that at least one universe would have the exact conditions necessary for flatness. This idea aligns with the anthropic principle, which suggests that we observe our universe to have certain properties, because these properties are necessary for our existence. In other words, we find ourselves in a flat universe because that is the type of universe that can support the formation of galaxies, stars, and ultimately, life as we know it. The multiverse concept thus provides a framework where our apparently fine-tuned, flat universe is not an unlikely coincidence, but rather an expected outcome in a much larger cosmic landscape. While this explanation is compelling, it remains a theoretical concept, as we currently have no way to directly observe or test the existence of other universes. The concept of a multiverse, the idea that our universe is just one of many, has gained traction among some theoretical physicists and cosmologists. While direct observational evidence remains elusive, several theoretical frameworks and observations provide intriguing support for this hypothesis. String theory, a leading candidate for a unified theory of physics, suggests the existence of multiple universes as a natural consequence of its mathematical framework. This theory proposes that our universe is just one of many possible configurations of fundamental strings vibrating in higher dimensions. The inflationary model of the early universe, which explains several observed features of our cosmos, also hints at the possibility of a multiverse. According to this theory, our universe underwent a period of rapid expansion shortly after the Big Bang. Some versions of this model predict that this process of inflation continues eternally in other regions, giving rise to countless other universes. Quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales, offers another perspective on the multiverse. The many worlds interpretation of quantum mechanics proposes that every possible outcome of a quantum event occurs in separate branching universes. While these theories provide compelling arguments for the existence of a multiverse, it is important to note that they remain speculative. The challenge lies in finding ways to test these ideas empirically, as other universes, if they exist, may be fundamentally unobservable from our own. The search for evidence continues, driving further research and pushing the boundaries of our understanding of the cosmos. Eternal inflation is a fascinating concept that expands our understanding of the universe's origins and structure. This theory suggests that the inflationary period of the early universe, a time of rapid expansion, never fully ended. Instead, it continues eternally in some regions of space while stopping in others. In areas where inflation has ceased, we find pocket universes like our own. These pockets form when quantum fluctuations cause small regions to break away from the expanding space. Each of these pockets potentially becomes a separate universe with its own physical laws and constants. This process of eternal inflation naturally leads to the idea of a multiverse. As inflation continues indefinitely, it generates an endless number of pocket universes. Each of these universes might have different fundamental properties, such as the strength of gravity or the nature of dark energy. This variation could explain why our universe seems so finely tuned for life, as it would be just one of countless possibilities. The concept of eternal inflation thus provides a mechanism for the creation of multiple universes, supporting the broader theory of the multiverse. It suggests that our universe is not unique, but part of a vast, ever-expanding cosmic landscape filled with an infinite number of other universes. Theoretical physicists have proposed several intriguing types of multiverses, each offering a unique perspective on the nature of reality beyond our observable universe. The quilted multiverse suggests that space extends infinitely, containing countless copies of our observable universe. In this model, given enough distance, we would encounter regions identical to our own, as well as variations where events unfolded differently. Another concept is the inflationary multiverse, where our universe is just one of many bubbles that formed during cosmic inflation. These bubble universes expand independently, potentially with different physical laws and constants. The brane multiverse, rooted in string theory, proposes that our universe exists on a three-dimensional membrane, or brane, floating in a higher dimensional space alongside other brane universes. The quantum multiverse, based on the many worlds interpretation of quantum mechanics, suggests that every possible outcome of a quantum event occurs, splitting reality into parallel universes. In this model, all possible histories and futures are real, existing in separate branches of reality. Lastly, the mathematical multiverse posits that all mathematically consistent universes exist, including those with different physical laws or dimensions. These multiverse theories challenge our understanding of reality and raise profound questions about the nature of existence. While currently unprovable, they provide fascinating frameworks for exploring the potential vastness and diversity of the cosmos beyond our observable universe. The multiverse theory represents a significant departure from traditional cosmological models, expanding our understanding of the universe far beyond a single, self-contained cosmos. This concept proposes that our universe is just one of many, perhaps an infinite number, existing simultaneously. Traditional models have long held that the universe we observe is all there is, with a single set of physical laws governing its behavior. The multiverse theory challenges this notion by suggesting that different universes might have varying fundamental constants, physical laws, or even dimensions. This idea emerged partly from attempts to explain certain puzzling aspects of our universe, such as its apparent fine-tuning for life. In a multiverse scenario, our universe's seemingly improbable conditions become more plausible, as it would be one of countless universes with different properties. The multiverse concept also aligns with some interpretations of quantum mechanics and string theory, providing a broader framework for understanding reality. While it remains a controversial and unproven idea, the multiverse theory continues to push the boundaries of cosmological thinking, encouraging scientists to consider possibilities beyond our observable universe. The concept of multiple universes, often called the multiverse, challenges our fundamental understanding of reality and existence. This idea suggests that our universe might be just one of many, perhaps even an infinite number, each with its own unique properties and physical laws. One profound implication is the question of our significance in the grand scheme of things. If countless universes exist, our own might seem less special or unique. This could reshape our perspective on the apparent fine-tuning of our universe for life, as it might simply be that we exist in one of the universes capable of supporting life among many that cannot. The multiverse concept also raises intriguing questions about the nature of possibility and probability. In a scenario with infinite universes, every possible outcome of events might occur somewhere. This leads to mind-bending considerations about alternate versions of ourselves making different choices or living in worlds with slightly different physical constants. Furthermore, the idea of multiple universes challenges our notions of creation and purpose. It prompts us to reconsider traditional ideas about the origin of the universe and our place within it. potentially shifting our philosophical and even theological perspectives on existence itself. Detecting or gathering evidence for other universes is one of the most challenging tasks in modern cosmology. Scientists have proposed several methods that could potentially provide indirect evidence for the existence of other universes. One approach involves searching for patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. Some theories suggest that if our universe collided with another universe in the distant past, it might have left a detectable imprint on this radiation. Astronomers carefully analyze this cosmic background for any unusual patterns or cold spots that could indicate such a collision. Another possibility lies in the study of quantum entanglement. Some physicists propose that quantum effects might allow for interactions between parallel universes. By examining the behavior of entangled particles, scientists hope to find anomalies that cannot be explained by our current understanding of quantum mechanics, potentially pointing to the influence of other universes. Gravitational waves offer another avenue for exploration. As our ability to detect these ripples in space-time improves, scientists speculate that we might one day observe gravitational waves originating from beyond our observable universe, providing tantalizing hints of other cosmic realms. While these methods remain highly speculative, they demonstrate the innovative approaches scientists are considering in their quest to uncover evidence of a wider multiverse. The shape of the universe is a dynamic aspect of cosmology that continues to evolve as our universe expands. Observations suggest that the universe is currently flat or very close to flat, but its ultimate shape and fate depend on the interplay of various cosmic forces. As the universe expands, its shape could change in three primary ways. It might remain flat, stretching out infinitely in all directions. Alternatively, it could curve positively, potentially closing in on itself like a vast four-dimensional sphere. The third possibility is a negatively curved universe, which would take on a saddle-like shape, expanding ever more rapidly. The driving force behind these potential changes is the balance between the expansion rate of the universe and the gravitational pull of all its matter. Dark energy, a mysterious force causing accelerated expansion, plays a crucial role in this cosmic shaping. If dark energy continues to dominate, the universe might stretch flat indefinitely. Current data favors a flat universe that will continue expanding, but the shape of the universe remains an open question in cosmology. Future observations and advancements in our understanding of dark energy and dark matter could reveal surprising twists in the cosmic tale of our universe's shape. The ultimate fate of a flat universe is a topic of great interest in cosmology. Current observations suggest our universe is indeed flat, making this question particularly relevant. In a flat universe, the expansion rate precisely balances the gravitational pull of matter, leading to some intriguing possibilities for its future. As the universe continues to expand, it will do so at an ever-slowing rate, but never quite stop. Galaxies will grow increasingly distant from one another, and the vast spaces between them will become larger and emptier. Over incredibly long timescales, even nearby galaxies will appear to recede beyond our cosmic horizon, leaving our local group of galaxies isolated in an increasingly dark cosmos. The fate of matter in this scenario is equally fascinating. Stars will eventually exhaust their fuel and die out, leaving behind cold, dense remnants like white dwarfs, neutron stars, and black holes. These remnants will slowly evaporate through processes like Hawking radiation, converting their mass to energy over unimaginably long periods. Ultimately, a flat universe faces a future often described as heat death or the Big Freeze. In this state, the universe reaches maximum entropy. All matter will have decayed, and the remaining energy will be spread so thinly across the vast expanse of space that no further work or complex structures can exist. The universe becomes a cold, dark, and essentially empty expanse, marking the end of all cosmic processes as we know them. Dark energy profoundly shapes our understanding of the universe's destiny. This mysterious force, which accounts for about 68% of the cosmos, exerts a repulsive effect that counteracts gravity. As the universe expands, dark energy becomes increasingly dominant, accelerating the expansion at an ever-growing rate. This accelerating expansion has significant implications for the far future. Distant galaxies will eventually move beyond our cosmic horizon, becoming permanently unobservable. The observable universe will gradually empty, leaving our local group of galaxies isolated in a vast, dark expanse. Some scientists speculate that if dark energy continues to strengthen, it could lead to a scenario called the Big Rip. In this potential future, the expansion becomes so violent that it tears apart galaxies, solar systems, planets, and even atoms. However, this remains a speculative idea based on our current understanding. Alternatively, if dark energy remains constant, the universe might experience a heat death or big freeze. In this scenario, the cosmos expands indefinitely, cooling until it reaches a state of maximum entropy where no work can be done and no life can exist. The nature and behavior of dark energy thus play a crucial role in determining which of these futures awaits our universe. The Big Freeze scenario is a potential ultimate fate of the universe, closely tied to the concept of a flat universe. In this scenario, the universe continues to expand indefinitely, gradually cooling down over an immense span of time. As the expansion progresses, stars exhaust their fuel, galaxies grow dark, and the universe becomes an increasingly cold and empty place. A flat universe, which current observations suggest is the most likely shape of our cosmos, plays a crucial role in this scenario. In a flat universe, the total energy density is precisely balanced, allowing for continuous expansion at a steady rate. This delicate balance means that the expansion neither slows down enough for gravity to cause a collapse, nor accelerates to tear everything apart rapidly. As the flat universe expands, matter and energy spread out over an ever-increasing volume. This leads to a gradual decrease in the average temperature and density of the universe. Over incredibly long timescales, even black holes would evaporate through Hawking radiation, leaving behind a sparse soup of fundamental particles. The Big Freeze does not mean a complete cessation of activity, but rather a state of maximum entropy where useful energy becomes unavailable for work. In this far future scenario, the universe would reach a state close to absolute zero temperature, with particles so spread out that interactions become extremely rare, effectively ending the universe as we know it. The shape of the universe is a fundamental aspect of its structure, and current observations strongly suggest that our universe is flat. However, the possibility of a transition from flat to curved is an intriguing question that touches on the nature of cosmic evolution. The curvature of the universe is intimately tied to its energy content and expansion rate. In our current understanding, the shape of the universe is determined by the balance between its matter and energy density and the rate at which it expands. A perfectly flat universe exists in a delicate equilibrium, where the expansion rate precisely matches the gravitational pull of its contents. For the universe to transition from flat to curved, there would need to be a significant change in this balance. This could potentially occur if there were dramatic shifts in the universe's energy composition or if unknown physical processes came into play. For instance, if dark energy, which currently drives the accelerated expansion of the universe, were to change its properties over time, it could potentially alter the universe's curvature. However, it's important to note that such a transition would likely occur over vast cosmic timescales, if at all. Current models of cosmic evolution do not predict such a change, and observational evidence continues to support a flat universe. While the idea is theoretically intriguing, it remains speculative and is not supported by current scientific consensus. Dark energy models significantly influence our understanding of the universe's ultimate destiny. The simplest model, known as the cosmological constant, suggests that dark energy maintains a constant density throughout space and time. This scenario leads to an ever-expanding universe that gradually cools and thins out, resulting in a cold, dark future often called the Big Freeze. Alternative models propose dynamic dark energy, where its properties change over time. Some of these models predict that dark energy might weaken, allowing gravity to eventually halt and reverse the expansion. This could lead to a big crunch, where the universe collapses back in on itself. Other dynamic models suggest dark energy might become stronger, potentially tearing apart cosmic structures in a scenario known as the Big Rip. Interestingly, some theories even propose that dark energy could decay into other forms of energy or matter. This could result in a universe that expands more slowly or even transitions to a contracting phase. The exact outcome depends on the specific properties of dark energy and how they evolve over cosmic timescales. The fate of the universe remains uncertain, and ongoing observations and theoretical work continue to refine our understanding of dark energy. As we gather more data and develop more sophisticated models, we may gain clearer insights into the ultimate destiny of our cosmic home. To understand the long-term evolution of cosmic geometry, scientists rely on several key observations. One crucial piece of evidence comes from measuring the cosmic microwave background radiation, the afterglow of the Big Bang. This ancient light provides a snapshot of the early universe, revealing subtle variations in temperature that hint at the overall shape and curvature of space. Another important tool is the study of Type Ia supernovae, which serve as cosmic distance markers. By observing these stellar explosions in distant galaxies, astronomers can track how the expansion rate of the universe has changed over time. This information helps determine whether the universe will continue expanding indefinitely or eventually collapse back on itself. Large-scale galaxy surveys also play a vital role in mapping the distribution of matter across the cosmos. These surveys reveal the intricate web-like structure of the universe, with galaxies clustered along vast filaments separated by enormous voids. The precise arrangement of these structures provides clues about the underlying geometry of space and how it has evolved. Gravitational lensing observations offer yet another avenue for probing cosmic geometry. As light from distant objects bends around massive structures in space, it creates distorted images that astronomers can analyze. These distortions depend on the geometry of space itself, allowing scientists to test different models of cosmic evolution and constrain the shape of the universe on the largest scales. Our ability to predict the future state of the universe is limited by several factors, including our current understanding of physics and the inherent uncertainties in long-term cosmic evolution. Based on our best models and observations, scientists can make reasonably confident predictions about the universe's overall structure and behavior for billions of years into the future. For the next few billion years, we can forecast with some certainty the fate of our local cosmic neighborhood. The Milky Way and Andromeda galaxies are on a collision course, expected to merge in about 4 billion years. This event will reshape our galactic environment, but will not significantly affect the larger structure of the universe. Looking further ahead, predictions become less certain. Current models suggest that the universe will continue to expand, with the rate of expansion influenced by dark energy. If dark energy remains constant, we might expect the universe to keep expanding indefinitely, leading to a scenario known as the Big Freeze or heat death. In this future, galaxies would become increasingly isolated, and the universe would grow colder and darker. However, beyond about 100 billion years, our predictions become highly speculative. The nature of dark energy, which currently eludes our full understanding, could change over cosmic timescales, altering the universe's long-term fate. Additionally, unforeseen phenomena or revolutions in our understanding of physics could dramatically change our predictions for the far future of the cosmos. The concept of a flat universe has profoundly impacted both philosophical thought and cultural perceptions. This idea, rooted in modern cosmology, suggests that the geometry of our universe is essentially flat on the largest scales. This notion has challenged long-held beliefs and sparked new ways of thinking about our place in the cosmos. Philosophically, the flat universe concept has reinforced the principle of mediocrity, which posits that there is nothing special or central about Earth's position in the universe. This has led to a shift in how we view ourselves in relation to the cosmos, encouraging a more humble perspective on our cosmic significance. It has also fueled discussions about the nature of infinity and the potential for parallel universes, as a flat universe could theoretically extend infinitely. In popular culture, the idea of a flat universe has inspired science fiction writers and artists to imagine vast, endless landscapes of space. This has resulted in stories and visual representations that depict the universe as an immense, open frontier waiting to be explored. The concept has also influenced discussions about the ultimate fate of the universe, as a flat geometry suggests the universe might expand forever rather than collapsing back on itself. The flat universe theory has also had implications for religious and spiritual beliefs. It has challenged some traditional cosmological models found in various faiths, leading to new interpretations and discussions about the nature of creation and the role of divine forces in shaping the universe. This has fostered dialogue between science and religion, encouraging a re-evaluation of ancient texts and beliefs in light of modern cosmological discoveries. Cosmic flatness, the observed shape of our universe on the largest scales, has profound implications for our understanding of our place in the cosmos. This property suggests that the universe extends infinitely in all directions, with no overall curvature. Such a vast, possibly infinite expanse challenges our perception of our significance and uniqueness. In a flat universe, our observable region might be just one of countless similar regions, each potentially hosting its own galaxies, stars, and possibly even life. This concept dramatically expands the scale on which we must consider our existence. It implies that what we can see and measure might be only a tiny fraction of what exists beyond our cosmic horizon. The flatness of the universe also relates to its ultimate fate. In a flat cosmos, the expansion is likely to continue indefinitely, albeit at a slowing rate. This means that over incredibly long timescales, the universe will become increasingly sparse and cold, with galaxies moving farther apart. Our cosmic neighborhood, once teeming with nearby galaxies, will become increasingly isolated. Furthermore, cosmic flatness aligns with the theory of cosmic inflation, which posits that the early universe underwent a period of rapid expansion. This inflationary model helps explain the uniformity we observe across vast distances and provides a framework for understanding the origin of cosmic structures. Thus, the flatness we observe today may be a relic of the universe's earliest moments, connecting our present to the distant past and future of the cosmos. The concept of an infinite flat universe challenges many traditional religious and spiritual beliefs that often depict a finite, structured cosmos. This scientific model, supported by observations and theories in modern cosmology, presents a universe without boundaries or a central point, extending endlessly in all directions. For some believers, this vast, limitless expanse might reinforce the idea of an all-powerful creator, capable of fashioning such an immense realm. Others might find that it contradicts specific creation stories or cosmologies central to their faith, which often describe the universe as having defined limits or a particular shape. The notion of infinity in space can also spark philosophical and existential questions about humanity's place in the cosmos. It may lead some to feel insignificant in the face of such vastness, while others might find it spiritually uplifting, seeing infinite possibilities for life and creation. Ultimately, the impact of this scientific concept on religious or spiritual beliefs varies greatly among individuals and faith traditions. Some adapt their beliefs to incorporate new scientific understanding, while others maintain a separation between scientific and spiritual worldviews. This ongoing dialogue between science and faith continues to shape our understanding of existence and our place in the universe. The concept of cosmic flatness has sparked numerous artistic interpretations across various mediums. In visual arts, painters and digital artists have created expansive, seemingly infinite landscapes that stretch to a distant horizon, symbolizing the uniform distribution of matter in a flat universe. These works often feature vast, empty spaces, punctuated by celestial bodies, representing the delicate balance between gravity and expansion. Sculptors have explored cosmic flatness through large-scale installations, using materials like mirrors and reflective surfaces to create illusions of endless space. These pieces invite viewers to contemplate their place in an immense, possibly infinite cosmos. Some artists have even incorporated interactive elements, allowing observers to experience the concept of flatness firsthand. In literature and poetry, cosmic flatness has inspired works that explore themes of vastness, uniformity, and the search for meaning in an expansive universe. Authors have crafted narratives set in universes where the laws of physics create perfectly flat geometries, challenging characters to navigate and understand their reality. Musicians and composers have also drawn inspiration from cosmic flatness, creating ambient soundscapes that evoke a sense of endless space and time. These compositions often feature long, sustained notes and minimal variations, mirroring the uniform nature of a flat universe and inviting listeners to lose themselves in the cosmic expanse. Our understanding of the universe's shape has undergone a remarkable transformation throughout history, profoundly impacting human perspective. Ancient civilizations often viewed the cosmos as a flat plane or a celestial dome arching over the earth. This limited view placed humanity at the center of creation, fostering a sense of cosmic importance. The scientific revolution challenged these notions. Copernicus proposed a heliocentric model, shifting Earth from the center of the universe to just another planet orbiting the Sun. This revelation sparked a fundamental change in how humans perceive their place in the cosmos, initiating a journey of humbling discoveries. As our tools and methods advanced, our cosmic view expanded dramatically. Edwin Hubble's observations in the early 20th century revealed that our galaxy was just one among countless others, further diminishing Earth's cosmic significance. The discovery of the cosmic microwave background radiation provided evidence for the Big Bang theory, suggesting the universe had a beginning and has been expanding ever since. Today, our best models indicate that the universe might be flat on the largest scales, potentially infinite, and expanding at an accelerating rate. This vast, dynamic picture of the cosmos continues to reshape human perspective, highlighting our small yet unique place in an immense and evolving universe. It challenges us to think beyond our immediate surroundings and consider our role in a much grander cosmic context. As our knowledge of cosmic structure expands, we are confronted with profound ethical questions that challenge our place in the universe. One key consideration is how we should approach the potential discovery of extraterrestrial life. If we find microbial life on Mars or Europa, do we have an obligation to protect it? Or does our scientific curiosity justify studying and potentially altering these life forms? Our growing understanding of the vastness of the cosmos also raises questions about resource allocation. Should we invest heavily in space exploration and potential colonization of other planets, or focus our efforts on solving pressing issues on Earth? This dilemma becomes more complex as we realize the incredible number of potentially habitable worlds in our galaxy alone. The concept of cosmic timescales and the ultimate fate of the universe also present ethical challenges. Knowing that the universe will eventually become uninhabitable due to heat death or a Big Rip scenario, do we have a responsibility to find ways for life to survive beyond our current cosmic era? This ties into questions of long-term species survival and the value we place on the continuation of consciousness in the universe. Finally, our expanding cosmic perspective forces us to grapple with issues of meaning and purpose on both individual and species-wide levels. As we recognize our small place in an immense and ancient universe, we must reconsider how we derive meaning and what our ethical obligations are to each other and to the cosmos itself. These questions will only become more pressing as our understanding of cosmic structure continues to grow. The concept of a flat universe has profound implications for future space exploration and colonization efforts. In a flat universe, space continues infinitely in all directions without curving back on itself. This means that as we venture further into space, we can expect to encounter new galaxies, star systems, and potentially habitable planets indefinitely. For space exploration, this implies that there will always be new frontiers to discover. Our telescopes and probes could continue to push the boundaries of known space, constantly revealing new cosmic structures and phenomena. This endless expanse of unexplored territory could drive scientific curiosity and technological innovation for generations to come. In terms of colonization, a flat universe suggests that humanity would never run out of potential new homes. As Earth-like planets are discovered in distant star systems, future generations might embark on long-term missions to establish colonies light years away from our solar system. The vastness of a flat universe could also necessitate the development of faster-than-light travel or other revolutionary propulsion technologies to make such far-reaching colonization feasible. However, the concept of a flat universe also presents challenges. The sheer scale of infinite space could make coordinating and maintaining contact between distant colonies extremely difficult. It might lead to the development of isolated human civilizations, each adapting to their unique environments and potentially evolving differently over time. This scenario underscores the importance of developing advanced communication technologies to maintain connections across vast cosmic distances in our future space exploration endeavors. The study of cosmic geometry offers profound insights into the nature of scientific inquiry and the limits of human knowledge. As we probe the vast scales of the universe, we encounter phenomena that challenge our intuitions and push the boundaries of our understanding. Cosmic geometry reveals the intricate structure of space-time itself, showing us how matter and energy shape the very fabric of the cosmos. This field of study demonstrates the power of mathematics and observational techniques to uncover hidden truths about reality that are far removed from our everyday experiences. One of the most striking aspects of cosmic geometry is how it highlights the iterative nature of scientific progress. Our understanding of the universe's shape and structure has evolved dramatically over time, from early models of a flat Earth to our current conception of an expanding universe with complex topology. Each new discovery builds upon previous knowledge while sometimes radically reshaping our worldview. The study of cosmic geometry also underscores the importance of technology in expanding human knowledge. Advanced telescopes, satellites, and computational tools have allowed us to peer deeper into the cosmos and analyze its properties with unprecedented precision. This reminds us that our understanding of the universe is intimately tied to our ability to observe and measure it, always leaving open the possibility of future revelations as our capabilities grow.